get to things such as a computational storage model, or perhaps even starting to approach in-memory type computing. And then we'll talk a bit about some of these emerging non-volatile memories, particular 3D crosspoint, which is a phase change memory, MRAM, resistive RAM, and I may make a few comments about ferroelectric RAM. I just had a conversation with the company doing that. And then we'll look at some of the energy savings with persistent memory, some of the reasons why they make a lot of sense, particularly on the edge and endpoints, some projections on persistent memories, and then a summary. So why these persistent memories are necessary is there's basic reasons. Flash in particular has issues of scaling. This is the linear scaling with lithography. 3D NAND flash went from planar to 3D when it's approached 15 nanometer lithographic features. And 3D, you're building stacks of memory cells on top of each other, but it's not cost effective in a CMOS logic process. NOR flash, which can work in the CMOS process, seems like it stops to scaling with FinFETs at about 28 nanometer. Smaller processes getting to more density of memory on the die need some new technology. And even SRAM, used in embedded applications, its scaling may stop at about 14 nanometers. DRAM, which is a very popular high-performance memory, consumes lots of power because it has to be refreshed often. So there's issues around that. And standalone persistent memory applications are growing, and low-power, high-density memory is needed for embedded applications, and also, as you'll see, for some data center type applications as well. So let's more on the emerging non-volatile memories. There's intense effort to commercialize several of these memories. Potentially could replace volatile memories such as DRAM and SRAM, and also be able to replace NOR flash, especially in embedded applications. And these technologies can be applied to standalone memory chips, as well as embedded memory. And this could reduce the energy expenditure, for instance, in a battery or power-constrained environment, and also create more efficient data centers. And these non-volatile memories will enable both IoT devices as well as data centers, and also at the edge and in the cloud. And the memory technologies, again, we're talking about are magnetic random access memory, resistive RAM, phase change memory, and ferroelectric RAM. So a little bit about these lithographic scaling. Semiconductor process shrinks have worked for decades to reduce costs, as is illustrated in the left chart. The process runs along the bottom, shrinking as we move to the right. That is the smaller lithographic features. The relative cost on the vertical axis has historically come down with every process shrink. But flash memory has a problem. It's unable to scale past a certain point. For NAND flash, again, that was 15 nanometers. So flash memory moved to 3D NAND. NOR flash, the only non-volatile memory currently used to store the code in microcontrollers, ASICs, and other system on chips, is unable to scale past 28 nanometers. Its cost declines, indicated by the red line, therefore cease at this point. So to address these issues, manufacturers are migrating to new memory technologies. These emerging memories are needed to allow further cost reductions. These emerging memory technologies are represented by the black line on the chart. They continue to scale to smaller and smaller features. Today, they're more costly than NAND flash, but they will eventually cost less than flash to produce since they can scale past 28 nanometers. Now, the chart on the right plots the cell size for SRAM cells that were presented at an IEEE conference over the past few years. Although the cell size, the vertical axis, has been shrinking to keep pace with the process geometry, running again along the horizontal axis, it suddenly seems to stop shrinking as the process transitioned from 22 nanometers to 14 nanometer. In addition, SRAM is much larger than many of the persistent memory candidates because it has so many transistors to make it operate. So here's we talked a bit about there's been new developments in the memory industry in general, in particular movement to NVMe type interfaces for solid-state drives, but there's other things that are coming along as well. And there's a group called SNIA, Storage Networking Industry Association, that developed a persistent memory programming model where, as you can see, there's various modes in which the application would be able to address memory, persistent memory in particular, that is non-volatile memory. And eventually, if you look in the far right, to have a direct memory, direct address to the memory rather than going through a file system or kernel or some other approach. And the development of NVMe enables new ways to access data. And the NVMe over Fabric, in addition to NVMe, extends this model across the network. And the remote direct memory access or remote direct memory access over Ethernet, which is RoCE, and other approaches to memory-like data access are enabled by these new networks. And emerging fast persistent memories will enable new computing models and greater efficiency by using this technology. Give an idea of the kind of things we're talking about here. This is from a SNIA Persistent Memory Summit, which is earlier in 2000, January 2000, where they're showing levels of support for interacting. And right now it's done with NVMe, but there's new interfaces that they're talking about, which may replace, for instance, the traditional memory bus. CXL is one of these, which would allow heterogeneous memories, that's not just DRAM, but various types of memories to work in there. So new coherent interfaces allow dealing with this persistent memory storage. But there's also a challenge to be worked out as well, again, in this software and other approaches here. But RDMA is remote direct memory access. We're using these new networked infrastructures built around high performance memory. I can address memory in another device like it's my own memory, and pool memory and do various other things because of that. Now, this is leading to ideas that may eventually lead us to this concept of in-memory computing, or at least memory-centric computing. Instead of moving data from storage to compute, the idea, and especially with the ending of scaling in the semiconductor processes on the logic units, where essentially Moore's law, Dennard scaling do not work the way they used to work anymore. People are starting to build new types of processing devices, domain-specific processors, that they can do specialized functions instead of having everything go through a CPU. And that's leading to new ideas like putting special processors that are in the memory, where you create this computational storage, for example, but also to create new types of fabrics that these processors can work on as well. You can see here where we have NVMe over Fabric for a storage fabric, and then a memory fabric, for instance, Gen Z or the CXL, depending upon whether it's in a box or between storage units. And so these ideas of this disaggregation of memory, that you can use memory, brings the storage closer to the memory, instead of having the memory. And the memory could be wherever it needs to be, and you bring the processing to it. You can also pool and share the memory, and then we can work with various heterogeneous compute environments, as well as different types of memory, DRAM and say phase change or 3D crosspoint memory, for example. Now, let's look at some of these candidates for persistent memory. There are many emerging memory types vying to replace, for instance, NOR flash, and they all share the same attributes. They all have a small single element bit cell that promises to scale smaller than current technologies in order to support small, inexpensive die and 3D stacking. They also promise to be easier to use than flash memory by supporting write in place with no need for a block erase, and they have more symmetrical read and write speeds. Finally, they're non-volatile or persistent. Data doesn't disappear when power is lost. They can all be used as persistent memory. So again, these technologies we're showing here. And looking at the development of some of these memories, MRAM is magnetic random access memory is one of these. And there's a company called Everspin, which makes standalone MRAM chips. They've shipped over 100 million of these chips for various caching, buffering applications over the past several years. They have a partnership with Global Foundries. They build the 300 millimeter wafers that Everspin gets, but the company Global Foundries is also targeting making products using MRAM and its embedded memory applications. And all the major foundries are starting to ship Spintel Torque MRAM products, or incorporate them in embedded products. And other examples, like IBM uses Everspin MRAM in its flash core modules that are used in its storewise and flash systems arrays. Another memory that's out there in use is 3D XPoint, which is a phase change memory. Intel Optane NVMe products began to be available in 2017. They introduced DIMM products in 2018. Both are used in modern storage systems. And Micron last year introduced an X100 NVMe 3D XPoint SSD as well, and claims to have customers. Now, the acceptance of an emerging memory technology depends on its pricing. To capture mainstream market, a memory must be cost competitive against entrenched technologies. This cost structure can be achieved through high volume manufacturing and shipments. Products that don't reach this volume must play in niche roles because of their higher prices. A good example of this is the Micron Intel 3D XPoint memory. The chart on the right represents a memory storage hierarchy. For a memory or storage technology to make sense in this hierarchy, it must be cheaper than the next fastest technology along the horizontal axis, and faster than the next cheaper technology on the vertical axis. So Intel has been trying to get 3D XPoint adopted into this memory hierarchy. It's faster than flash, but slower than DRAM. But to fit in the hierarchy, as is shown in this chart, it must be priced below DRAM. Otherwise, Intel's customer will just buy DRAM. Although Intel probably lost well over $1 billion per year on Optane 3D XPoint over the past 3 years, it may be starting to get closer to break even because the volume is up now. And again, to reiterate, a technology like 3D XPoint must be cheap to sell in volume, but on the other hand, 3D XPoint must sell in volume to get cheap. So there's kind of a chicken and the egg problem there. And the same problem stands in the way of other emerging persistent memories acceptance. So let's take a look at some of the things that are driving people to look at MRAM as embedded applications. MRAM saves power while reducing the chip size and cost. Embedded MRAM will shrink smaller than SRAM and flash. A 1T, 2T MRAM bit cell is smaller than a standard 6-transistor SRAM bit cell. And NOR flash hits a scaling limit again after 28 nanometers. MRAM could replace embedded SRAM and NOR since it offers lower power, lower cost, and higher density. And just to show you some examples, this one and actually the next one are both products out of large, perhaps the largest foundry, TSMC. This is in these products, microcontrollers, ASICs, and other SoCs will lead in the use of these persistent memories in embedded devices. And one of TSMC's customers, Ambic, is developing chips that will enable the next generation of battery-powered, always-on voice recognition IoT endpoint devices. The company's 4th generation Apollo SoC family sets new standards for low-power, intelligent endpoint IoT devices. It's implemented with TSMC's 22-nanometer ULL process. It has power use as low as 3 microamperes per megahertz using MRAM memory. And you can see here, in fact, there's 2 megabytes of MRAM along with 1 megabyte of SRAM. And that's one example. Another one, and this again is a customer made by a customer of TSMC, is a company called Numen, and they have a deep neural network MRAM accelerator chip that they've used. You can see here where they have this MRAM memory unit in their product, and with this accelerator shrinks the memory by about 2.5 to 3.5 compared to SRAM because it's a much smaller bit cell, so I can get more memory in the same space, or I could have a smaller space overall for the die. So a significant reducer eliminates DDR memory access by having more memory on the chip, resulting in lower power and lower latency. And it requires about 20x less standby power. So this actually is programmable using CUDA-C, so NVIDIA's language and its compiler. And important, particularly there, NASA is wanting to use these chips for distributed computing for space applications, partly because MRAM is radiation hardened and has high endurance, and it also is non-volatile. Some other interesting technologies. Now we're moving into a little bit about resistive RAM. Resistive RAM and also phase change memory are being extensively investigated for use in artificial intelligence applications. They particularly lend themselves in linear weighting configurations in an architecture commonly known as neural networks. And they're a very simplified type of inference engine that can perform an enormous amount of math at low precision in a very short time. A simplistic view of the network, maybe you can see kind of on the left-hand side where all these things are networked together. Now, a few of these resistive RAM companies, there's standalone companies. Dialog Semiconductor acquired Adesto Technologies in June of this year, and they're shipping what's called CB RAM technology. And they're also they're going to license that to global foundries. They're offering Dialog's product as an embedded non-volatile memory option. Another company, ARM, announced a spinoff of Surf Labs to develop and license new types of non-volatile memory based upon correlated electron materials and also ferroelectric transistors. Here's a little bit more about the TSMC announcements, which are both resistive RAM as well as MRAM. They say on the resistive RAM side, they have 40 and 22 nanometer resistive RAM ready for production as an E-flash, that NOR flash alternative for IoT and smart card applications. They say it can get up to 10-year retention at 125 degrees after 10,000 cycles. And they have a number of customers that they're going to do tape outs in the second half of this year. Their 22 nanometer MRAM is also ready for production. Particularly, there's a target on automotive qualification that they think will be done by this quarter. And 16 nanometer, that's a 22 nanometer MRAM. At 16 nanometer MRAM, they're talking about risk production for an E-flash-like product in the fourth quarter of next year, and a DRAM type in the fourth quarter of 2022. This shows some of their use of resistive RAM for these low power applications and these power management integrated circuit devices. And they use it again as the embedded NOR flash replacement. Now, there's benefits in these persistent caches. Some of them are lower energy consumption because it's non-volatile. You don't have to refresh it. When the power goes off, it's still there. They also can provide faster transactions, especially if you can do processing on a chip versus using an external memory. And these things can provide significant value for data center embedded system applications. And here's some examples here to understand how greatly persistent memory, and even SSD is an example, can reduce system energy consumption. Here's a study from Carnegie Mellon University, Penn State University, Intel, and AMD. This is one chart from that study. Compares the energy consumed for 6 programs on 3 types of systems, one based on hard disk drive, one on SSD, and one that uses persistent memories for storage. The study breaks the memories down in much more detail, but we'll just show this high-level view here. The GEP4 program that has the lowest savings still uses 35% less energy with an SSD than with an hard disk drive. If we move from SSD to persistent memory, it provides an additional 45% energy savings. So altogether, compared to the hard drive, that would be an 80% savings over the hard drive system. Note that this is the program that was the least impacted by using non-volatile fast memory. Now, these power savings can be important, and perhaps the most difficult issue facing many hyperscale data centers. The use of non-volatile cache memories can result in less data movement, leading to faster processing and lower power consumption. Some modern data centers are being built near intermittent low power sources, such as wind farms, as represented in this figure, which can run complex but non-time critical operations. These data centers may be pausable, stopping processing when the wind power stops. And using non-volatile caches will allow fast recovery of operations when the power resumes. Replacing volatile cache with non-volatile memory will enable faster recovery when there is a power loss in the conventional data center as well, and that can reduce the need for backup data center power. In embedded products, higher an embedded system using processors with internal cache memories, for instance, cell phones, autonomous vehicles, high-end instrumentation, for instance, like the MRI scanner pictured here. For energy-constrained system running on batteries or in harvested power, the energy savings of frequent power down modes using persistent cache memory can multiply the battery life. MRAM and resistive RAM scale better than SRAM, so given chip size can have more of that memory than SRAM could. More memory can store more data and thus lead to fewer cache misses, and subsequently, fewer slow accesses to memory. This improves performance, also saves the energy from moving that data. In applications such as AI inference, often done at the application endpoint, can require significant cache memory. MRAM or resistive RAM can give you more memory available on a given die area, allowing smaller die for the SoC and thus lower die cost, or more memory and more capability to process. Now, here's projections on the growth of some of these new memories, particularly 3D XPoint, that's the Optane and MRAM. This is from a report that a fellow named Jim Handy and I have done for a few years, and we're looking at MRAM and 3D XPoint growth. You can see the petabyte growth here, but also they could generate $36 billion in revenue by 2030. This shows how the shipment growth could drive that number. And this includes both embedded as well as standalone MRAM. And the assumptions made here are embedded MRAM replaces most SoC NOR and SRAM, and that MRAM has strong appeal for AI applications. So just some summary: lithographic scaling is limiting the use of NOR flash and possibly SRAM for high-density embedded devices. These persistent memories that scale beyond NOR flash and SRAM are now available. They will change our hierarchy. And MRAM will grow for embedded low-power applications. Persistent memories will eventually replace SRAM cache memory as well, I believe. And that'll improve performance, decrease power use from data center to embedded devices. And MRAM and phase change memory use will generate over $36 billion in annual revenue by 2030. So with that, here's some information on this report I spoke about. And I'm open to questions. Thank you.
Thank you very much, Tom. That was a very informative session on a lot of upcoming technologies and upcoming memories. Very nice to know about the MRAM for AI ML. That is something I'm pretty sure a lot of people are going to be interested in, because AI ML being the buzzword of the century, if I'm not mistaken. Do we have any questions? Let me just take a look. But I don't see any questions at the moment. But if we do have any questions, we will be passing them on to you so that you can take them up offline, maybe.
Okay, I will stop sharing. I will stop sharing here. There we go.
Thank you very much, Tom, for that very informative session about the upcoming emerging persistent memories that we are going to look at in a few years now. With that,
so Anvit, so I had a question for Tom, as in two questions actually. So one is you mentioned about the RRAM being more suitable for the neural networks and AI. So the first question being, so what properties do you see the memory should exhibit if you want to make it more useful for AI kind of workloads or neural networks?
So the neural networks are using these, they're using it for weighting functions. So the size of the memory is going to be important for these applications. Also, in some of these memories, actually, there's some resistive memories that actually work better as they get smaller in size. They actually have better, larger differences in resistance, and therefore, better signal for the change to be able to detect the bits and that sort of thing. So those are important characteristics. The size of it's very important, because the whole idea is you want to have a bunch of these cells that can interact with each other and change their weighting functions based upon the inference training they're getting. So good response times, are important. Fast writing capability, lower power for writing would be important in that case. Good endurance is important, because you're going to be, doing a lot of writing if you're training, almost continuous writing and training, and then having being able to scale to small sizes as well. I think those are all important characteristics for these neuromorphic type memories, which a lot of which are being they're talking about using resistive RAM or phase change memories to accomplish.
Sure, thank you. And Tom, a follow-up question, not a follow-up, but a separate question is, often I see some trending on quantum RAM or QRAM. So what are you seeing, like any trends, developments? Is it still a buzzword or some progress on that front?
Are you talking about quantum computing? Is that what you're talking about? So
yes.
Qubits? Oh, okay.
Qubits,
so,
yeah.
Yeah, so qubits, so when I'm talking about these persistent memories, these are memories that retain their data even after the power is off, and they can do it for a fairly long period of time. The problem with quantum computing, if we're talking about the same thing, is that it generally operates at cryogenic conditions, and it requires requires, say, quantum entanglement, and that tends to decay fairly quickly over time. So the big trick with qubits is trying to keep them coherent for a long enough period of time to be able to carry out calculations, and especially with a bunch of qubits working together to do a calculation. It's a different issue than in the case of these non-volatile memories.
Sure. Thank you, Tom.
Thank you, Ankit, and thank you, Tom. This is a virtual event, so we will be presenting you a virtual memento. Thank you from everyone here at the IEEE Data and Storage Summit.
I will accept it. Thank you.
Thank you very much. All right, then, with that, we have an interesting... Oh, thank you so much. Yeah, thank you. Okay, then, we have an interesting panel discussion coming up. It's going to be on data and storage next. Let me welcome the panel members: Narayanan Subramaniam, Technical Director from Nutanix; Rochelle Alvers, Storage Management Architect at Intel Corporation and Board Advisor at SNIA; Stephen Tan, Board Chair at Soda Foundation; Nilima Ghani, Senior Engineering Manager at Hewlett Packard Enterprise; and moderating the panel will be moderator Ankit Mathur, Chief Architect Storage at Huawei. Over to you, Ankit.
Thank you so much, Anvit. Hello, everyone. Good morning, good afternoon, and good evening, based on wherever you are. Since it's a virtual event, it's good that we have people connecting in from across the globe and without the pain to travel and come and join in person. So welcome to the panel discussion. We will be talking about the data storage next. I am Ankit Mathur, Chief Architect for NAS Storage at Huawei in India, and I have been with the storage industry for over 16 years, and my stint includes close to 13 years with NetApp, and where I've been dealing with NAS, unstructured data protocols, and ecosystem. And of late, during my work with Huawei, I'm also sort of interested in high-performance computing, but from the storage point of view. And I will be the moderator for this panel discussion. So again, some rules of this panel discussion game. So the audience, you can hear us, you can see us, but we can't hear you. So to make it more interactive, I would request that you use the chat box or the Q&A box, and you can address the question to the panelists. So now let me introduce, first of all, Narayan Subramaniam. So he's the Technical Director for System Management in Nutanix. But prior to this, he has a very rich experience in the telecom domain and end-to-end stack of servers, SaaS, and then his foray into the storage and hyperconverged. So welcome, Narayanan. Sorry. So as a leader in system management, going forward, what do you see as the key challenges and trends with the multiple heterogeneous storage systems and compute systems and their deployments?
Yeah, sure. Audible?
Yes, we can hear you fine. No, so there is some radio, we are seeing some glitch.
Good morning to everyone. Are you able to hear me now? To hear me now?
Yes.
Okay, maybe I'll turn off my video for a while. Is that better?
Yes, Narayanan, this is better.
I'm in case you can't hear me or there's some audio jitter. All right.
Sure.
Yeah, so thank you once again for having me in discussion this morning. And thank you, Tom, for a very enlightening talk on different types of memory technologies. Really appreciate that. So for your question, Ankit, so given that, analysts and perhaps definitely Tom for sure, I'm a relative newbie into storage, right? But what I come in is with a lot of diverse experience in system manageability, right? So your question really around challenges and trends on storage and compute system. I mean, I've worked on various aspects as from an engineering standpoint as well as from a consumption standpoint. So if I was to summarize a few of the things, it would be as follows, right? I mean, one thing that generally one sees in the system manageability domain and is it is crucial for technology adoption of products, right? How well a product is engineered, finally it has to be deployed, lifecycle managed, updated in the data center, and so on. And technology adoption really relies on how it's easy to map specific use cases for technologies, right? So I think Tom gave some very nice use cases on different memory technologies, how they could be applied in different domains. So that's a crucial part, right? If you're to abstract it at a higher level, where is HCI relevant? Where is non-volatile memory storage technologies most relevant? For example, right? Those are use cases. Data models, right? This is a ever persistent problem, not just in storage, but across all industry verticals, be it on the telecom, networking, data center servers, IoT side. This is a consistent problem that I have seen, is data models. Now, while standards are important, I think it's also important to note that consistency in being able to model extensions to standards. That's where business makes money, right? Standards is great in terms of providing a common interface, but differentiation comes and which requires modeling and consumption extensions. Another challenge that I see is when we look at consumption models, right, for storage or compute, right, in terms of APIs, in terms of data models, very often you find that the consumer is expected to consume the internal data model, which frankly requires a PhD in computer science to understand. You look at DNA, which have been around there for data centers for a while, or if you look at typical MIBs, the old type of networking, or if you look at more complex models of late, the internal data model is somewhat exposed to users. What would really be needed is a level of tiering where what's exposed to users is easily consumable, right? Everyone talks about user experience, and user experience is not just limited to UI. It is increasingly.
I think you're right. Like increasingly of late, what we saw with the adoption of cloud. So one thing that cloud brought in was you don't really need to be a system administrator or a storage administrator. You could be just an app developer.
That's
and
right.
You could just pick up some space in the cloud. You don't know where it actually resides. You don't care how it is protected, and you're just a consumer. So I think one of the reasons, even I agree, that cloud picked up was the simplicity in managing things.
But I still think it needs to go a long way. A lot of complex data models, it needs to be further simplified. I think some companies in the consumer space, for example, guys like Twilio and so on have exposed a lot of APIs for the integration, so on, done a really good job in simplifying voice and video access APIs. Right? The other sets of problems that one deals with in storage or in computing is, I think engineers as such or architects as such, we are very focused on all these initial stuff, features, APIs, and so on. But one thing which becomes a huge challenge, which is often neglected, is the ease of troubleshooting, debug, diagnostics, what it means to operate these products at scale in data centers. So while we look at standardization for consumption, for features and functions, I think it's also important to look at what are common trends or common candidates for data models which can be used in ML AI algorithms, which are increasingly used for anomaly detection, capacity, forecasting, trending, classification of different applications based on data types, and now which is the increasing holy grail of how to troubleshoot between the application to network, compute, and storage infrastructure. Right? There are a couple of companies which are really focused on that because that's the hard problem to solve. Finally, customers want application issues, right? And they need a way to easily troubleshoot the bridge between the three, right? And finally, I mean, if you really look at it, There are other areas related to the ease of life cycle management and migration and so on. Again, these are neglected problems. I feel they come mostly as an afterthought. And I think the trend that you see is, system manageability is unfortunately in two parts. One is the initial part where there's a lot of focus on UI and ease of use. But the second part, which is the harder part of lifecycle management, troubleshooting, diagnostics, debug, automation of that, adoption of DevOps principles, even at design phase to address stuff, is somewhat lacking. So this is a common problem which I've seen. I've seen this in the SaaS environment. I'm seeing it today here, even in the storage, or even in the IoT space, which I was in before joining Nutanix, right? So this is a common theme across. So I'll stop here.
Sure. I know it's close to your heart with your sessions on Agile and DevOps and things. So I would request to hold on to your thought, Narayanan, while I bring in other panelists into the discussion. So let me take the pleasure to introduce Nilima Ghani, who is a Senior Engineering Manager at Hewlett-Packard Enterprise. And Nilima brings us over 31 years of industry experience with almost 21 years put at HPE. Is that right?
Yeah, that's right.
So, yeah, so big stalwarts in the storage in the discussion today. So she has been working on operating systems, hyperconverged file systems. So let me ask you, Nilima. So the AI in the storage data management, it has come a long way, or is it just a buzzword? So what do you see as trends and challenges in the adoption of AI in storage today?
Yeah, I think that's a great question, Ankit. Thanks. I think there is a very strong trend for adopting AI really aggressively. So there are two aspects to this. One is the actual, data, customer insights and analytics, right? Which basically are really important to, for example, predict potential issues that the customer could hit, right? Things like anomaly detection and a lot of these predictive kind of algorithms. So that is from the actual, how it helps the customers in managing their infrastructure, right? That is one aspect of it. The other aspect is when we talk about edge to core to cloud, right, which is nowadays really gaining a lot of traction, right? And in terms of, being able to enable more compute decisions to be made at the edge, right? Because there is this huge cost or involved in data mobility across edge, core, and cloud, and more, we want to see how what kind of analytics can be done at the edge itself, and so that is a more contained kind of area for the customers, right, in that space.
Yeah. So when you say like lots of data being generated at the edge, so immediately I start thinking about autonomous car driving, wherein with so many sensors and each car, there was some stat like it generates few gigs of data on each car in a certain amount of time. And if all of that data were to come to the data center, maybe we don't have enough bandwidth as of today. So
Exactly.
yes.
Yeah, and data is just exploding, right? So that is one example. As we were talking earlier as well, social media itself, right? So much of information coming in from that space. So I think being able to intelligently, make those decisions at the correct points in this whole edge to core to cloud ecosystem. That is becoming really important, and that's something where analytics play a very big role. And basically, those are the aspects that I wanted to talk about. And we are, of course, hearing of, some of the technologies that Tom talked of, using these persistent memory technologies, where, due to the large capacity and performance benefits, more and more, use of analytics for big data, using the persistent memory technologies, right? So in that sense, the information that the data that's actually coming into the data center, if you will, right? So that's where some of these big data analytics, etc., play a big role. So that's something that I wanted to talk about.
Sure, sure. So let me get the other panelists on board as well quickly, so that everyone can jump in and contribute to the point at hand. So I take the pleasure in welcoming Richard Howlers, who is Storage Management Architect at Intel and Board Advisor to SNIA. And prior to Intel, Richard had been with Hewlett-Packard for 20 years, Broadcom for around 5 years, working on manageability, external storage, NAS, management and protocol standards, and I think of late also on CXL management. And well, I see her as the face or evangelist for the SNIA Swordfish work all along, right? So, yeah. So, so having control over all aspects of the product flow, and basically the companies can have control over everything they are manufacturing. They don't really need to coordinate with someone else. They own the ecosystem, and they can grow a big way. But we are increasingly seeing a shift towards open communities for data storage and management. And I think this question is probably close to even Stephen Tan, who is our fourth panelist for today. So, Rachel, just hold on to that thought while I introduce Stephen as well. So, who is the sort of foundation chair and also VP and CTO for cloud solutions for FutureWay in the Bay Area. And he leads the efforts in open source and interface with data and storage management. And he has been the strongest pillar in pulling off Soda Foundation, and now it's a big wave. So you not only have lots of storage and other vendors as part of it, you also have, interestingly, Toyota, which is actually a car company, and Yahoo from Japan, also part of the Soda Foundation. So welcome, Stephen. So yeah, back to you, Rochelle. Coming back to the question on why is there a shift to the open communities at all? Why would vendors actually want to shift to sharing and making them interoperate so much?
Okay, thanks. That's a great question. So I think folks that have been in the industry for a long time are familiar with the role that standards at play. Are you guys hearing me okay? I know my audio has been doing really weird things today. But so standards have been around for a long time and clearly at the protocol layer. But when you get up into the management space, it gets a little bit more nebulous. One of the things that has been a concern in industry for a long time has been how long it takes to develop standards. And as technologies have been moving very fast over the last few years, we've seen in some of these emerging spaces, cloud, hyperscalers, others, groups get together to say, here's best practices. As a way to try and counter this perception that standards take too long. Well, one of the things that's been happening in the background is that standards have actually started to move a lot faster. One of the things that we're doing with the SNIA's, SNIA Swordfish work, with the DMTF, and with some other standards is actually move to provide updates to those standards 3 or 4 times a year instead of having them be on 1 or 2 year release cycles. So there's what we're seeing with the open standards and with communities like SODA that Stephen can talk about is partnering with them to actually have the open communities work to provide the kind of the use cases, if you will, very abstractly, and say, this is what we want to build, and partner with the organizations to really provide the standards and specifications that they can build on. So we find that to be a really good working model moving forward. And as you know, Stephen can talk about some specifics about how the SOTA Foundation is actually working in the open source space and partnering between open source and standards.
So, yeah, both Rishal and Stephen, do you want to add upon, like, then what's the value add that vendors could bring in if you standardize the entire flow? So is it then a cookie cutter? I could just buy anything off the shelf and it just works the same. So why would you buy it from me or from someone else?
That's an excellent question. This is all about how you position standards. You buy standards have a place in basically in multiple levels, right? So from a protocol perspective, you want standards there so that you can, plug things in, from a physical perspective, so that things plug in and interconnect the same way, and you have commonality there. That doesn't mean that everything is the same. What it does is allows you to figure out a way to make your product and focus on the differentiation points. So you can think of it as I focus on the actual functionality that differentiates me from my competitors, and whether it's a hardware product or a software product or a combination, that's where you should be focusing. You shouldn't be trying to spend all your time focusing on functionality that everybody has to providing and trying to do that in a different way, because that does a disservice to your customers. Vendor lock-in by proprietary means ultimately does you a disservice and does your customers a disservice, because you should all be focusing on, I want this product because it's got better functionality, it's got better capabilities, and that's why I want it in my environment.
Sure. Stephen, do you have something to add in there?
I totally agree with Michelle. So in terms of like standardization, what's actually important is actually the interoperability. I mean, the part here is to enable, to serve your customer essentially. So what you want to do, like most what Michelle just covered, vendors need to differentiate, in terms of like the performance, like scalability and stuff like that, and not things like how do you create a volume? Everybody needs to create a volume. Why do you need to have your own protocol to create your own volume? So that part is, these are basic things. If basic things have already been covered, there's a standard for that. Everybody follows that standard, and then the vendor tries to differentiate. In terms of like making things better in terms of the different feature sets that they have. Yeah. So what I wanted to add is that what's more important actually, to add to what Michelle was saying, having a standard is not enough. The adoption of the standard by vendors is also important. So to get vendors to do things that they don't want to do is hard. So vendors actually have all kinds of different priorities. Okay, so trying to follow a standard is actually probably the last of their priorities. Unless there's a very what do you call it, a very good motivation for doing that. And the motivation obviously is going to come from users. If users were to push, like say they need a standard or they need all these things to work together, then vendors, and that's the best motivation for vendors to to get something done. So in SOTA Foundation, what we are trying to do is essentially this. We try to, we embrace standards like SNEAR, Swordfish, and so on that Michelle, has been spending many years working on. So we embrace those kind of standards that have been done. SOTA Foundation, we don't try to set standards. If there are standards out there that that's already being pushed by some organization. We think it makes sense. We try to integrate that within the projects that we do. So in Soda Foundation itself, what we try to do is that we try to build an open data framework that leverages all these standards. And what we need, I mean, what we want to try to do is essentially what the earliest speaker, I think Nilima was saying, you know, how do you actually connect data from the edge to the core to the cloud? How do you provide the connectivity for, like, if users want to run Kubernetes kind of applications, you want to run big data, AI, or machine learning kind of stuff? I mean, the data framework needs to support that kind of stuff. And you need to have like data management policies for things like data protection, data lifecycle, and data security. So that's where all the different kinds of standards that are out there that we try to, you know, integrate within the framework itself. And also this framework ultimately, I mean, what it tries to do is to break down silos, right? So that there's no data fragmentation. Everything is like connected. All the data is connected. So again, I mean, to do these things, standards is going to be, I mean, whether it's de facto standards or industry standards, I mean, ultimately we need some kind of standardization there. So again, I mean, to do these things, we need all the different vendors to work together. So in Soda Foundation itself, what we try to do, I mean, that's what we try to do. We try to provide a neutral platform or forum for all the different vendors to work together. So we have like companies like Intel, IBM, Fujitsu, Huawei, Scalarity, Sony, and recently Seagate just joined us. So a bunch of companies already, I mean, getting together to work on these things, and we definitely welcome other companies to join in. And like what Ankit was saying earlier, Soda Foundation is kind of like, it's an open source foundation under Linux Foundation, but it's slightly different in the sense that actually our focus here, unlike some of the foundations, like our key focus is actually our end users. So we have like end users like Toyota, Vodafone, you know, KPN, China Unicom, China Railways, and you know, companies across the different regions and different industries that are part of this. And the reason that they need to be, or they want to be part of this, is because they want vendors to come together to help them solve their problem. So instead of them, you know, working with each individual vendor to solve their problem, they prefer to have like an open platform, so that there's no vendor lock-in. I mean, everybody can collaborate openly, and that's what I mean. This standardization and open source kind of efforts come together for data and storage management.
Sure, thank you, Stephen. So, well, Narayanan, Stephen didn't name your company, but yeah, so you have dealt with this from as a user and as a developer contributing products into the space. So what's your set of thoughts on this? Like, do you see that you can still be able to create that extra value, that even if you were to stick to the standards, but then still customers will actually vie for the product you have developed?
Yeah, I mean, earlier, right? I think standardization provides a common base or common platform for interoperability is one thing. One is at the protocol space, right? So I think that's a done thing, right? Then in terms of features and functions which are exposed to the customer, right? So, you know, standard models and standard interfaces, APIs, so to speak, for orchestration, they definitely help to set a common baseline. And you know, depending on how the standards are matured over years and the speed of standard maturity, right? Different companies adopt them at different trends. I've seen this in over the last 10, 15 years, right? If standards take a while to evolve or they're complex to understand, usually companies tend to put them aside for a while till they mature, right? Because it takes time for you know, the internal software architecture sometimes to rejuggle itself to serve the common data models and the common APIs. I mean, that's the reality, right? It's one thing is to have a model on paper, the second thing to actually go implement it. And usually companies in this in implementation, right? Because the model may not be performant based on different use cases that somebody may have, right? And I'm talking predominantly from consumption, from API consumption models. One part that needs to be handled, and where unique features, where companies differentiate is unique features and value adds on top of that, right? And that is where the models need to be easily be extensible, right? And where you don't want a silo of one model for a common framework for doing standards-based interfaces and a parallel silo for custom features and functions, because some of them are add-ons or integrate to the core feature in itself, right? And that's where sometimes the challenge comes in, right? As to what one would do. So you'll find companies saying that, hey, I'll adopt this standard, but I'll do this spec, and this spec. But these other 4 or 5 specs, although there's a standard model for that, but there are a lot of custom extensions I'm going to deviate, right? So there's no right answer about this. I think each one is right from their perspective because they have to differentiate, they have to provide value to customers. At the same time, you want some common level of interop, right? For operations perspective, right? And I think we need to stop just having a developer engineer centric view. We need to also have an operation centric view, right? How people want to integrate products, right? Because the people who operate data centers are not core designers, right? From a pure software perspective, their outlook and approach is different. Right? So these are the challenges that I see. I think standards are great; they serve a purpose, but let's also not be, if I was to be a little not a controversial standards. Let's not be naive in assuming that standards alone are nirvana. I think we are going to have a lot of customizations and extensions, and that's how companies compete, right? And that's the reality of business and reality of providing feature sets. Nobody wants to be commoditized, right? Everyone wants to add value.
That's true.
Yeah. So, Ankit, if I may.
Sure, Nilima, please go ahead.
Yeah. Just hearing folks talk, some things which came to my mind, right, which is probably of interest, is with this shift towards as a service models, right, where a lot of the and this is customer driven, right, where they'd rather have something as a service than kind of invest heavily in something that's on premise, right? And so as a service, and then software defined kind of becomes really important there, right? Because what is underneath is probably not of any concern for the end user, right? End users only seeing a service presented. And so some of these areas, kind of are good candidates for some kind of standardization, where, as Stephen was saying, that, basics are taken care of. Things like security, which is really important. Things like also reliability and stuff like that, right? And some of these, I think, are really important areas as we are seeing kind of pivots towards as a service kind of technologies. That's something I just wanted to add.
You're absolutely correct, Neelam. There are more security standards in flight right now than at any time I can ever think of. 10, 15 years ago, there were a lot of companies doing what I will term security by obscurity in their management stacks. That is not first of all, that's not security, but that's also no longer acceptable. there are multiple standards organizations working together on defining security at multiple layers of the system: protocol security, management security, transport security, and working in the model that I described earlier, where we have organizations like OCP, the Open Compute Platform, defining use cases and then working hand in hand with organizations like DMTF, the PCI SIG, to add additional levels of instrumentation into those protocols to help instrument those use cases.
Right, Rachel and Nilima, we are seeing increased policy enforcements as well. Like a lot of people might name GDPR, but then there are data privacy and data control laws coming in China and India as well. And US also has its own share of data control laws. And with the enforcement, I think companies have a responsibility to prove that they are actually complying. And as you rightly mentioned, the security by obscurity probably is no longer an available option in these scenarios.
Yes, companies don't just have an obligation, they have a responsibility to provide secure systems in an ongoing, increasingly secure, and to develop products using a security development lifecycle in addition to your software development lifecycle. So you should be looking at security through the entire development lifecycle of your product.
That's right.
Absolutely. Yeah.
So switching gears, so some of the newer technologies which even Tom mentioned about in his talk. So Nilima wanted to hear your views. So how do you see the storage and compute deployment architecture reshaping with non-volatile memories across the different deployments in data center or elsewhere?
Yeah, that's a great question, and I think very much in keeping in with the theme of this conference as well. So I view it more as like a storage memory continuum, if you will, right? Which is different things for different people, right? And when we talk about delivering efficient storage and some of the proprietary kind of use cases where there's a lot of focus on the security and having control, etc. A lot of these traditional customers, right, they are still very much tied into storage, right? And they, obviously the slower adopters of newer technologies. But I think what I'm saying is, there is definitely space for everybody, and we're seeing, a lot of emerging trends where companies are doing hard pivots to, some of these new technologies, right? And talking about, so, just as an example, like Rachel, we were discussing earlier, that tape has not gone out of business even now, right? So we still have, the traditional customers, and, rightly so, right? Depending on their use case. At the same time, we are seeing an emergence of, the newer use cases, have a very strong adoption of hyper-converged technologies. And of course, the hyperscalers are, totally leading the way with their, the way they are kind of utilizing newer technologies. And we are going to see more and more kind of a convergence, storage and the compute, right? So the trend is already there, and server attached storage, especially where you get horizontally scalable storage due to the software defined, is already out there. And then we have NVM, NVMe, and NVMe OF. That these are only speeding up the shift, right? And I would say that I wouldn't say that this is the death knell of traditional storage, right? Definitely not. But at the same time, there is also a lot of focus on adopting the persistent memory technologies. One thing which probably just talking about the data, like I was talking a little about the edge to core to cloud, right? Where we have IoT and edge, which is basically processing the data in motion. Essentially, that's where data is acquired and it's queued, routed, orchestrated, right? And there is some kind of analytics happening there. But then there is also the, and then there's fast data, which is the movement of data into the core, if you will, where there is a, analysis, a much deeper analysis of data at rest. And those are probably the areas where technologies like NVMe, etc., are really very useful to do big data analytics.
So Nilima, one point, like what I call the NVMe dilemma, right? That sort of bothers me is that, like even Tom referred to it, that the persistent memory or like the Intel Optane or others are actually so pretty fast. They are just like maybe 10 times slower than the RAM. And what it means is that if we are talking about distributed systems, like most of our systems are no longer scaled up single big box. So if you have to even visit the box next door, or maybe just in the same rack, if you're going out of the box, you are incurring a cost over the network, and that's physics. Like it will take you longer to get to the next persistent memory deployed on another box. So how do you see that shaping up? Because if I have to have a distributed system on one end, because I need to scale out, I need to have vast amounts of data and compute, but then persistent memory is fast, and then you might actually end up asking, why should I put something so fast? Because when I get to it, I actually incur other costs which are making the fast persistent memory actually futile. And I think I'll open it to other panel members also to jump in. What's their thoughts on it?
Yeah, I think that's a great point, in terms of speed, in terms of cost, and these are all the trade-offs, right, that really matter. And I think with some of the, like I was mentioning, the, if you look at the core, essentially, where the big data kind of, if you look at it, that's where it resides. And that's where, a lot of the undergoes a lot of transformations and restructuring, etc. Deep learning. So those are probably, good candidates for some of these persistent memory kind of technologies is what I, at least my view. And it could be that for the other use cases where, maybe you don't really need this kind of power, and maybe the traditional offerings make more sense.
Sure. So anyone else, any thoughts about the persistent memory world?
All right, can I get unmuted there? Yeah, I think Neela captured, quite a few use cases where we're seeing a lot of applications for persistent memory is really in, the cloud data center environments, and as well as in AI, as we figure out some of these, these high compute, high compute intent, highly compute. I'm not saying that very well. Applications. So there are a lot of kind of custom workloads that you'll see that AI kind of is a weird way to encapsulate those that are going to be able to exploit that that sweet spot for persistent memory. It does have a different price performance point, and you have to look at what workloads actually make sense for that. So that's why you see things like cloud and AI popping up and saying, "Oh, you know, that's a good fit for persistent memory," because you have to look at what the price performance points are that match that. So environments that are very flexible and have a lot of potential ones can also bring in persistent memory and get the key value out of that. You're not going to see it in a lot of necessarily general purpose or really very highly variable environments right now because of kind of you're trying to hit that sweet spot from the price performance perspective right now as the technologies are ramping up. Once it's a little bit more ubiquitous, you'll see it used a little bit more broadly. And also as you see a little bit better integration into the manageability stacks and into as it gets a little bit more tightly coupled with as applications become persistent memory aware, then you'll see also, because as databases go, ooh, persistent memory, I know how to exploit this, then you'll see a lot broader use for those workloads as well.
Sure. So let me switch to another aspect. We talk about performance, we talk about how fast we can go, but then one aspect I think a lot of us have ignored for way too long, but I think it's a topic that's close to heart for Narayanan, is the greener compute and storage. So is that actually a problem for only the edge deployment devices where they lack battery and power, or is it something that you see as a key behind the driving force behind like the whole new architecture and deployment all across?
Yeah, in my opinion, I think it's an all-pervasive problem. You know, it's a much larger topic. Actually, I'll be talking about that tomorrow in my session tomorrow for half an hour before the concluding of this conference. The topic is on green net storage and energy efficiency. So I'll probably reserve a bulk of my comments for that. But in summary, I think if I was just to summarize it in just one line, it could require a lot of grounds up architecture and design incorporation. And the reasons for that I will probably detail out in my session tomorrow. But it's not just limited to storage. I think it's the entire ecosystem that runs ICT and runs the internet that needs to be looked at. Right? Storage is just one element. It's a critical element, but it's not the only one. And so I'll chime in more on that tomorrow.
Okay, so let's take a pause and look at some of the questions that are coming in from our audience so that we can answer that in time. So let me just look through what are the set of questions here. Okay, so there is a question from Santosh Paul. With the edge exposed of tons of data, especially in image processing workload, is there any technological innovation happening at edge to make it cost effective and faster?
Yeah, so that is classic problem, right? How do you kind of intelligently process images, for example, right? Because there's not much one can kind of infer from that kind of data, right? So there is I wouldn't say that there is like a lot of offerings here. Typically we have the file capabilities. So when you talk of traditional storage, you have object, file, and block, right? And some of our file technologies have proved to be much more useful in terms of processing this data and making it available. So if the question is around, what might be a good solution with respect to, when we come with storage or some of the newer NVMe, etc. So I would say that probably, some of our, earlier technologies for filers, basically, those would be quite useful. That's my view here.
Yeah. I think there's some potential for some technologies there that might not be fully formed yet. So computational storage, to build on what Neelam had just said about, what some of the existing technologies are, computational storage would be a great concept. There's for this kind of a use case, it's still, I'll call it in the emerging technologies space would be probably the best way to describe it. It's really kind of the APIs and the use cases for it are still developing. There's a few companies that are in the early stages of trying to roll some products out. But this is really the kind of thing that they're looking for, which is we have product that might be storage and might be here, and we have, we can offload the computation, offload computation to these devices rather than having to do all the computation on classic compute side. We can offload it into the storage, and in an edge style configuration, potentially do this. But what we have to do in that space is really say, okay, what's the workload, what's the API, and really flush that all out before that market can be solid. So there's probably some other things like some of the innovations around 5G that are adding some new lighter protocol standards to help transfer data back and forth faster in those configurations. So there's a lot of potential different technologies that can help optimize these configurations, not necessarily specifically around the image processing workloads, but around workloads in general.
And what I wanted to add was actually at the edge, the storage will be limited. I think capacity is going to be limited. Yeah. In terms of the storage cost, is going to be, it's not efficient. So essentially, data at the edge needs to be managed properly, and what needs to be, filtered out, we filter it out, and what needs to be moved to the edge, to the core or to the cloud. There needs to be better management, data management and integration between the edge and the core, and also to the cloud. So that's going to be important. So, like for example, for like the Toyota car platform that we understand that there is a need for, how for the data lifecycle management from the edge to the core, and then when it gets to the core, it could be running things like machine learning, and then data gets stored there. In some primary storage, and needs to be moved to like secondary storage or moved to the cloud after that. So, so this kind of data lifecycle management needs to be there, for from the edge to the core to the cloud. Yeah.
Yeah, and Ankit, just to add to that, just drawing some lessons where I worked in the electric mobility field for about 2 years, right? And specifically charging and electric vehicles. There is such a mix of data that is coming in, right? There is video data, and there are a variety of sensor data, very low level, very frequent stuff that comes, for example, via CAN interfaces when batteries are plugged in, or pressure sensors, temperature sensors, humidity sensors, fire and smoke, and so on, and the video feeds, right? Is somebody tampering with the equipment and stuff like that? So there is a huge range of use cases, right? And each specific type of use cases, unfortunately, the edge presents very conflicting requirements, right? And coupled with the need of, does that system need to operate autonomously independent of the cloud, right? Now you'll have a lot of systems that need behave or operate autonomously independent of whether the cloud system or cloud compatriot is available or not. And it may not just be for a couple of minutes, it may be for a couple of hours or a couple of days even. Right? The electric mobility space is one such domain where this is really prevalent. So there is this tussle between cost and performance, and some of the things that Stephen mentioned earlier, right? What you keep locally versus what you transport out to cloud. What data needs to be local for local actions versus what needs to be done for post-processing at large scale. These are all real issues, and I think that, I think what I find is, my opinion is, every vertical solution will find specific needs for their own solutions, right? By working with vendors. I think it's sometimes difficult to cookie cutter, or peanut butter spread at one solution fits all. I don't think that's going to happen. The energy domain is different. Healthcare, IoT has different needs, and so on.
Yeah, I think one of the requirements I would add is also the reaction times at things. Like you mentioned about someone trying to fiddle with equipment, and you want to react quickly rather than send the data up, run a job in the background, and then process it. You want
can't do
instant
any
action.
of that. For example, for some of the things, anomaly detection, which requires some amount of data, has to be done locally and near real time, right?
Right.
Patterns have to be studied near real time. You can't afford to go to the cloud or wait for connectivity and things like that.
Right. And actually, if someone is really sabotaging, that's the first thing they would serve the link to your central cloud place or whatever, and then go about doing things.
Yeah. So I think different domains have very different requirements, and even within a domain, they are conflicting requirements. I mean, this has been my own personal experience in the IoT space.
Sure. So let me touch upon another question from the audience. And I think this is closer to what, Rachel, you have been working on, I think around the CXL. So the question is, any security standards in the memory-centric architectures?
Yes, actually, that's rebuilding on that, what I was talking about earlier with the security. Actually, several of the security standards that I mentioned earlier in that work is actually being applied into some of the new, the new memory standards. So CXL, which is the working in both aggregator and memory memory pooling kinds of environments, is built on as an extension and on top of PCI, so it's able to leverage some of those same kinds of things I was talking about earlier. Gen Z is actually using leveraging, which isn't quite memory architecture, but it's just, the same kinds of technologies. They're all leveraging a lot of the same security standards that we're building on top of initially the inbox communication layers. So, but we're leveraging and trying to, make things in a very common way across a lot of different technologies so that we're not reinventing the wheel again. So leveraging the same basically command set or protocol set and layering it on different technologies. So starting with things, starting with USB onto PCI, and this is the management command set, not the data transport, but USB to PCI. And so leveraging that across the PCI SIG and working and developing that in the DMTF, which is defining it from a manageability perspective. And then taking that back into, up to, the intent is to take that up to the CXL transport as well. And so that's, at least one of them that's going to be coming up into that space. They had that same group of people was already looking at how do we apply that to Gen Z environments. So you can see that same protocol set is basically proliferating out into a lot of different standards and different environments, using basically the same mechanisms. So, which is good, because if you find a hole in one, you found a hole in all of them, and you can patch it the same way, which is the benefit of standards, right? So, not so much good that you find the hole, but that you can, but that you've got a lot of eyes on it, and that you can kind of fix it. And fix it consistently. So, and there's a lot of players in that space. Weirdly, we have, this was a group that started with all your major server vendors and infrastructure, and folks building that kind of thing. And we had people starting to join that were doing things like, going back to Ankit's, one of Ankit's favorite things to talk about, building CAN networks in cars because of the security work. And they were really interested, so they started participating because they wanted to be able to take this same security protocol and apply it to those configurations as well. So it's very common and applies to all of those configurations.
Sure. And there is a related question, and I find it interesting as well. And I think we have the right set of people in the panel to answer this one. So it's about standards. So it's cooperation of multiple companies, and some companies may choose to join in later, let it mature more, and some of them have a big influence in the standards. So how do you make sure that it's not really biased towards one of the companies who's participating more intently or maybe throwing in more money, and gyrating the whole standards way towards maybe one or two players? So how does the standards remain sort of neutral that everyone can play, or someone can push in a standard in a way that only a particular company has the technology to implement those?
Well, as someone who, is the primary editor and author of a standard, let me take a stab at that, and then anybody else feel free to weigh in. Some of it is a mindset. When I am working on a standard, and I'm working for part of the standards organization, I have to explicitly make sure I am not simply representing my company. Part of that is a standards organization or a consortium. You are fundamentally representing the industry as a whole. You are making sure your company's use cases are represented, but when I am in that room, I am, my role changes. So the other thing is that industry associations, consortiums have minimum requirements for engagement. So to start a group within SNIA or within DMTF, you have a minimum number of companies that have to, promote the technology, that contribute to the technology, and that need to remain engaged in developing the technology in order for that to continue. If it drops below a single threshold and says, only one company is continuing to contribute, red flags go up. And if something is too heavily dominated, the organizations watch for that. Because, antitrust, collusion, all of those things are very bad. We don't like that. In general, we all know that it's the best, it's the right thing to do for companies to have something that's well balanced and is not skewed entirely towards them, because other people won't adopt them. If I go in and I write a standard that only works for my product, nobody else is going to use it. If we want multiple players in there so that we have something that actually works and that people are going to implement. So I'll stop there and see if, what anybody else wants to weigh in on that.
So this is the same thing for.
Yeah, go ahead, Stephen.
Okay, sorry. So the way standards work and open source works is the same. I mean, it's basically a group of different companies or representatives from different companies that come together to collaborate together. So each representative actually represents his or her own company, okay, and try to have a voice in there. But ultimately, a group, working together, collaborating together, has to get things done together. So there are things in place like governing boards, technical committees and stuff like that will actually oversee a lot of all this like proposals and stuff like that, or standards. And in the case of open source, the software that gets in there, there's like committees, and there are all kinds of different work groups that actually oversees the work, the architecture, the features, the roadmaps and stuff like that. So that's how standards and open source, work. There are different kinds of governance or governing bodies within the organizations that actually ensures that there's no single vendor that tries to dominate, or because it doesn't I mean, it doesn't benefit anybody if it's, I mean, a single vendor, driving something. I mean, end users are not going to use it, and the different other vendors are not going to support it. So it'll be the end of that organization if that's the case. Yeah, that's mine. Sorry, just go ahead.
Yeah, I mean, adding on to this, I mean, standards is for the greater good, right? So I think people coming together for a common purpose, and there will always be healthy tension between folks who are parts of standards bodies, as to develop eventually what becomes for the greater good, right? And now through the governing councils and through voting systems and all that stuff, I think that healthy tension gets leveled out into what's for the common good, by and large.
Sure. So we are sort of at the top of the hour, and today in our panel discussion, we touched about open standards, we touched about the persistent memories and conflicts and the edge, and coming to the core and to the cloud. So any final set of thoughts from any of the panel members? Anything you want to express before we wrap up? There are actually a lot of other questions that are there in the chat box, but I think in the interest of time, we might have to engage with the panelists offline, I guess.
Yeah, I don't know. We didn't really touch on 5G and things like that. I think that version of data that eventually would come in from connected devices, perhaps an important consideration at some point of time, perhaps in this or a future conference. I'm sure experts in storage have their own, valuable insights to share on how we are going to deal with that. The dimensions of scale for that, I assume, would be remarkably different from over the next 10, 15 years.
Absolutely. There's going to be some great and fun challenges as we take all of these new technologies, throw up all we know about storage management and managing all that data into the air, watch where all the cards land, and then pick them all up and figure out, how to sort them all out and figure out all the new use cases. And well, let's look, everybody who's working in storage, this is all just job security for all of us.
That's right.
Interesting thought.
Yeah, so I think.
Go ahead, Nilima.
Sorry.
Go ahead.
No,
go
I
ahead.
was just I was just probably just going back to what I was talking about earlier as well. As we talk about data mobility and all these aspects, having some kind of standards really makes sense, especially since there will be a lot of commonality across platforms from different vendors, right? Having thinking in that direction definitely helps. So I agree with Rochelle when she says it's a mindset, it's a collaborative thing, and I think it's all for good.
That's right.
Thank you, Nilima. Stephen?
Yeah, I just
you have the last minute.
I just want to do a little advertising. So for those, I mean, they are more interested in like in Soda Foundation and the projects that we're doing. We are going to be holding a SodaCon virtual conference, which is a 2-day conference on December 9 and 10. So I think the time is very India friendly. I think it's in the morning in India. So if you'd like to know more about the projects, and we're going to have like speakers from all the different, I mean, it's not only the Soda Foundation community, we're going to have like other folks from other open source communities, like Kubernetes community, CNCF, OpenStack, and so they're going to be there. And also Rochelle is also one of the speakers on the at the SodaCon event. So you're welcome to join, register, is for free. So if you're more interested in that, go to the sodafoundation.io website to check it out. Okay, thanks.
Yeah, so that was the elevator pitch from Steven, and do save your date on December 9th and 10th.
That's right. Yeah.
All right. So thank you, panelists. Thank you so much, Narayanan, Rachel, Nilima, Steven. I think we had a great set of questions and good discussion today. And thank you so much, participants and the audience, for staying around, asking some interesting questions. Thank you all. Back to you, Anvit.
Thank you, Ankit, and thank you to our esteemed panel members. It was a brilliant discussion, a lot of new things to hear, and it's always good to see feedback from so many people from different parts of the industry and different kinds of work that you've done. So thank you so much for your thoughts. With that, we will now move on to the next session. We have a few questions which were already asked, but due to the paucity of time, we are going to be posing them to the panel members, and then maybe we'll get back to you, or we can connect you directly with the panel members. With that, let's move on to the next session for the day. This is the first session for the day, in fact, which will be conducted by Zheng Yong. Zheng Yong is Senior Architect from Huawei, and the session is end-to-end near data process from big data engineer to distributed storage. Zheng Yong, over to you. You are muted, Zheng Yong. Could you please unmute?
Okay, it's okay now. You guys can hear my voice?
Yes, we can hear you.
Okay,
See your
good. Yeah, let me share my screen. Okay, 1 second. Okay, 1 second. Okay, can you see my screen now?
Yes, your screen is visible and you're visible as well. Please go ahead.
Okay, good. So, contrary, if we are trying to introduce some new technologies into the product to help the customer. So, including some NDP and some stream technology, but my today's topic will be focused on NDP. So we are in today's session we will have a look at some end-to-end NDP from the big data analysis engine to distributed storage. So I want to dig into some detail, but we are keeping some high level to see what we need to consider when we apply NDP into distributed storage. Okay, so let's move to next page. So for NDP, let me take 1 second to give some brief introduction about NDP. So NDP is not a new technology, right? It's this technology has been applied in some traditional database. We have seen this technology applied in some conventional products in the market, such as in some Oracle database. And this technology was introduced to solve the I think there are one key problem for this technology to solve. It's the bandwidth between the computing node and also the storage node. So in order to avoid some invalid data transfer between computing and also storage, NDP was introduced maybe several years ago. And in the left picture, you can see a simple picture. It illustrates how NDP can solve some problem from the limited network bandwidth. So one typical scenario is, for example, you want to do one select query from circle, and if you have 10 terabytes data, you have to, in traditional way, you have to read the 10 terabytes data from storage side into a computing node side, right? So usually for most customers, the bandwidth between these two different rows of node is limited, such as you can assume it's 10 gigabytes per second for the network. So for this 10 terabytes, you need to take 1,000 seconds for transfer, right? And if we take NDP to push down the operator or push down some calculation from the computing node into storage node. The data, assuming the data is, you only need such a 10 gigabytes. So you don't need to transfer 10 terabytes, right, from the storage side into the computing node. You just need to scan the data on storage side and also then send back the 10 gigabytes. So the time for this is only 101 seconds. So that's the difference. So from this picture, you can see, I think if NDP need to work well, it needs two conditions. One condition is the network bandwidth between the computing and also storage node, right? The second condition is your operation only need part of data, If in this scenario, if you still need 10 terabyte data for your computing, then NDP won't help you. So I think that's two conditions for NDP to work well. And so far in industry, we usually see three kinds of NDP. The first is, we call it PIM, process in memory. For this mode, it's usually push the computing computing task from the CPU into memory, and usually it's a special memory. It can do some computing. Okay, so usually you need to push the some computing task from the memory to from the CPU to memory to solve the bandwidth between the CPU and the memory. And the second is usually is ISM. So usually it's just like the word shoot, right? So this means you push some computing task from the computing into storage side. And the third one is ODDP. That means on disk data processing. That means you push the computing task from the CPU into the disk where your data is located. So today we just focus on the ISP in storage processing, and also after we apply NDP into storage side, we are considered to push down further, push some computing task further from the storage side into the disk, into disk to do some on disk computing. So in today's session, we will focus on the second ISP in storage processing. And in big data, usually, as I mentioned, NDP has been applied in some commercial products in such a traditional database. In big data analysis area, we also see some NDP, see some simple NDP implemented in the community such as Hadoop, Spark, and some components from Apache. Okay. So usually in big data analytics industry, we usually customer will use such a Hive to do some data house analysis, and also take the customer might take Spark Circle to take OpenLooken. OpenLooken is one open source project from Huawei, and it's based on Presto, and it do some optimization over Presto to do the circle-like analysis. So usually for this kind of engine, it needs to read huge data from the disk into computing task. And then they do the filter, they do the projection, they do the predictor calculation in the computing engine side. That means on CPU side. Okay, so in this engine, we see community introduce some operator pushdown, such as predicate operator pushdown from the engine side into the data format connector layer. So this kind of implementation can solve some problem. It can avoid some invalid data transfer from the bottom from the storage side to the up layer computing side. So it's just as sure as they left the picture. You can see in community usually they take the native HDF as they distribute storage, and usually the computing node and also the storage node they take the converged mode So usually computing engine and also the storage service, they are located in the same node. So with this push down, the data only need to read from the data node to the such a node manager. It's used by Yang to do the computing. So it only consume the bandwidth from the local AO adapter. It won't consume the network bandwidth from between one node and another node. So usually in this kind of feature, we can see the one popular pushdown is predicate pushdown. I just gave one example, such as you run the circle command select star from table 1 where age is larger than 16, right? So predicate pushdown, that means push the calculation age larger than 60 to 60, push this operator from the engine layer into the storage layer. Okay. And also another kind of popular pushdown is aggregation pushdown, such as the count star. That means you want to count the record number for your condition. So count is one kind of aggregation pushdown. Okay, it's one kind of aggregation. So usually in the community we see these two kinds of pushdown operator, and almost most popular engines support this, such as the Hive, Spark, Impala, Presto, and OpenLookan. All these engines support one or two of this pushdown. Okay, and in big data area, usually we will take special data format to store the customer data, such as you might take ORC, you might take POCUT, you might take carbon data. They are special data formats. It's not text format. It's all these different formats. They store data in different way in the storage. So they will write down some such as index information in different data formats, such as you can get some high level index information in the head and the bottom in one ORC file. So when in the community, when they push down this operator into the such ORC connector, such as the popular connector, this connector can filter the invalid data out before they send the data back to the engine. So this can help to save the CPU resource, save the memory resource used by the engine. So this is the situation from the community, and if we look outside of the community, you can see in most commercial product such as no matter it's Huawei or it's from EMC or IBM, they take different way. Usually they don't take a native HDFS. Usually they take the old commercial storage product, and they do some implementation. They take different way. So usually they will provide the special Hadoop connector, or they implement the HDFS protocol to connect the storage into the Hadoop or Spark ecosystem. So usually for this way, the storage box is from the commercial company. So usually we want to run the analysis engine over the storage node. So in this mode, it's a disaggregate architecture. That means your computing node is located on different node as the storage node. Okay, so it's shown by the left picture. So in this picture, usually for most customers, the network bandwidth between the computing platform and the storage layer, usually they take 10 gigabit, and that's a network. So the bandwidth between this computing node and storage node is limited by this network. And also usually we have small storage node, but we have a lot of computing nodes. That means maybe you have 10 computing 3 storage node, right? So this way, this disaggregate deployment, it solves some problem from the convergent mode. such as you can scale your computing resource, flexibility, and also you can scale your storage capacity separately, right? You don't need to scale the computing and storage together. So this mode has its advantage, but it also brings some disadvantage when you want to do some huge data analysis. So usually that's impacted by the network bandwidth between your computing platform and also storage layer. Okay, so that's the problem. So let's have a look at the NDP in the discrete architecture. So the left picture is from the converter mode. It's used by the community such as native HDFS. Okay, so the push down is the operator push down. The operator push down is pushed to this layer, into this layer, and this layer will read all the data from the native HDFS. Usually, it's located on the same node because native HDFS provides data locating, and also for HDFS client, it will first read the data from the local data node. Okay, so with data locating, if the operator is pushed down to this layer, it only consumes the local AIO network bandwidth. Usually, this will be very faster than the Ethernet network. So for the community, they push down to this layer is okay. But if we take the disaggregated mode it's shown by the right picture. If we only push down the operator here, we still need to take HDFS client to read all the data from the HDFS server. Usually this is from the commercial storage. So we still need to transfer the data, all data from this storage side into the computing side. So because the bandwidth between this computing node and also storage node, the bandwidth is limited. So usually this will impact the performance of our NDP in disaggregate architecture. So that's the that's the initial purpose for us to introduce some NDP into our product to solve the problem for customer. Okay, let's go to next page. So in this page, we will have a look at the overall for the NDP in this from the analysis engine to storage. So in the top, it's the analysis engine. It could be Hive, Spark, OpenLooking, Presto, maybe Impala like that. Okay, they will run the operator on the they were usually when you input one circuit language or circuit command, it will translate that circuit command into different computing stage. Such as stage 1, you need to read the data from table 1, such as stage 2, you need to read the data from table 2, and stage 3, you need to do some join from the table 1 and for the data from table 1 and table 2. So it will compile this SQL command into different plans, such as logical plan, such as execution plan, and for each plan it comprise of different stage. For each stage, it will comprise of one or multiple operator. So for the engine, it need to recognize which operator can be pushed down. Okay, so this should be changed by the analysis engine. So we hope in this layer, we hope the unified NDP framework can it's better to for us to have no change or minor change in the engine layer, because this engine layer is controlled by community, right? Usually it's difficult for one change specifically for one kind of storage to be accepted in the community. So if we have no change or have minor change in the engine side, that will be easy for us to push put some change back into community. And it's better to merge this kind of change into the mainstream, because usually for customers, they will purchase this layer from the other vendor, and they purchase the storage from the different vendor. So if they change for NDP or not in the community mainstream, that means for most customers they can't apply this kind of technology, right? So that's for the analysis engine we hope we can achieve this two purpose. And after the analysis engine, it needs to call some interface. It needs to call some API to do the NDP pushdown. So under the analysis engine, we need one layer. This layer, we call it NDP engine layer, okay? It needs to provide the NDP interface for the analysis to do the pushdown. And also it needs to do some pushdown cost evaluation. That means it's not every operator pushdown can benefit the performance. Sometimes, just as mentioned at the beginning, if your operator needs the total data from the storage side, then you push down will just waste some time in the such as scheduling, such as the communication from the engineering to the analysis engine to NDP engine, right? So we need to do some cost evaluation according to some rule, according to some policy, or according to some special algorithm, okay? And after it's decide, okay, it's if we push down, the operator can benefit the performance, then we need to do the push down. That push down will call the NDP interface, and this kind of interface need to talk with the NDP server. NDP server, this should be set up in the storage side to receive the request from the NDP engine. So we need to push down this request, and for this request, we need to schedule the request over other storage node, right? We need to usually you have multiple more than 10, more than 100. Maybe you have a lot of parallel tasks running over the computing node, and maybe most of them will do the pushdown, and then your NDP service will receive a lot of requests from the engine. Then you need to queue them. You have to schedule them one by one, and you need to consider the resource, such as CPU resource, such as the memory resource from different storage node, to see which node is okay to run this operator. So for this NDP service, it need to receive a request from a lot of computing node, and also it need to schedule the operator over the different storage side node. Okay, this is the overall picture, and for the unified ADP layer, we need to consider 3 points. 1 point is we need to have one connector layer for different engine. If we can have only one connector, that would be great, right? But usually different engine have different implementation. So maybe finally we need to provide different connector for or plugin for different engine, and also we need to do unified pushdown optimization and cost evaluation to decide that we need to do the pushdown or not. And the third one is we need to have some interface to talk with the storage side NDP service. And in the NDP storage side, we need to consider the overall schedule. This schedule need to provide a low latency, and also it need to consider some schedule optimization, such as maybe consider the data location. If you have a lot of metadata operation, we need to schedule the operator into special nodes like this. We need to do some optimization in task scheduling. And also for the operator, it still need to access the data, right? So we need to provide the fast data access. Usually it's not recommended to take the standard protocol here, such as NFS or such as HDFS, because for this protocol, they have some protocol cost. So we usually for the operator, we need to consider, we need to consider some fast data access implementation for operator to access data from storage side. And also, after the operator is done, we need to send back the data back to the analysis engine, right? Okay, so that's a, and in the future, when your implementation, the pushdown and storage side, we can consider offload the operator into the hardware, or offload the operator into the on-disk data processing. So this could be done in the future after we implemented the pushdown to storage side. Okay.
Zhenyang, would you want to take a sip of water maybe? Maybe we can look for some questions till then.
Yeah, there are some questions. Let me stop this.
If not, you can just take a break maybe, because I feel you're having a little trouble speaking.
Oh yeah, it's no problem. Okay.
Okay, all right then.
Okay, next page we are we have a look at some common NDP framework. So as we mentioned, we need to provide different plugin or connector for different engine for them to do the push down, and also we need to do cost evaluation. In this cost evaluation, so far we didn't see some open source implementation, so we need to do some we need to design some such as context in optimization according to the history circuit execution to check if one NDP is okay to do push down. Okay, this we have mentioned before. And for the push down cost evaluation, so NDP is not for every NDP to do push down. Just as we mentioned, for the original way, it will consume some network, right? So if the network is bandwidth is not limited for your circuit, or usually if your circuit command don't need a lot of data to consume the network bandwidth, for this kind of NDP, it might not be it might not okay to push down to the storage side, because as we mentioned, we need to queue the NDP request here. We need to schedule that out, right? All this will introduce additional latency for the operator. So if you NDP is will need all data, or if your NDP need most of data, we need to evaluate if it's okay to push this operation down to the storage side. So usually we if the operator needs just maybe such a 10% or 100% of total data, then that will be okay to do the NDP push down. Okay. So for the push down cost evaluation, we need to consider all this. Okay, let's go to next page. So NDP scheduler, we still need to consider this. So for NDP scheduler, usually we it's if we implement one scheduler, really it's a huge work because you need to provide a good scheduler engine, and also you need to do the resource consideration, right? So it's just like show this picture. Maybe for this node, it's busy, and it's take a lot of CPU utility. Maybe it's have few free memory. Then we just need to schedule a few tasks over here. But for this one, if it has a lot of idle CPU or idle memory, then we can push more tasks over there. So usually for this engine, we can consider take some open source one, or we can take some such as container-based scheduler, such as Kubernetes. Okay, it's one of option for most implementation. So we need to consider this.
Zhengyong, we are almost at the end of the session time, but we have a few questions. At least one that I have here from Supratim. So the fast data access for operator, is this interface also needed to be standardized?
We hope we can standardize this, but you know the different companies have different implementation. So far we are trying to look for some cooperation from the community. So we hope we can make this as a standard interface. But that's our purpose, our goal, right? But we still need some efforts to make this as a standardized. Yeah. But so far we are working with some community to do this. Yeah. Any other question? I think we have only lost 2 pages. So
yeah, I think we are almost on time. So maybe some closing remarks or thoughts. If you could just get there, that will help us. If you have just 2 slides, maybe you could just quickly wrap up.
Yeah, that will be quicker. So this is the overall flow for the NDP pushdown. You can see it's just a workflow for this pushdown. It's a save the pushdown and also data sent back to the engine. Okay, we need to consider this thing. Okay, this page, I think this is the last page. Okay, so for the operator, it's running over the storage side, and usually we don't embed this operator execution into the storage service. So usually this will be done maybe in separate process or in container. But for this operator, it need to access the data in high speed. So this need to consider. It's not recommended to take HDFS or NVLink protocol. We need to consider take some private interface for operator to access data in high speed. Yeah. Okay, I think that's all consideration for the NDP in the big data analysis. So let's look at some question if you guys have.
I believe we don't have any questions other than the one I asked at the moment. But if you do get any, there is another question here, and it says, using NDP ISP, we are saving on the network latency and demand for higher bandwidth. But what consideration to be made to avoid storage node resource crunch for avoiding bottleneck? Will the NDP in storage node not affect the performance?
Yeah. So usually we for storage side we will take we usually at least we have two networks. One network is for the standard protocol to access the data for the application. Another network is for storage node for the intra communication between storage nodes. Usually that network will have high bandwidth, such as for product. We have 10 gigabits for the external application, but we have 25 gigabits or maybe 40 gigabits for the communication between the storage node. So for the NDP, when we run the operator, we will take the storage network. We don't take the application network. So that can avoid the network consumption and to solve the bottleneck between the computing and the storage node, right? And yeah, as for NDP accept the performance, yeah, that's why we need to do the cost evaluation. We need to consider that. It's not every NDP could be pushed down because we need to consider performance. Yeah.
All right. Thank you so much, Zheng Yong. That was a very informative session indeed. And this is a virtual memento for you. Thank you for joining us on this, the IEEE Data and Storage Summit, and sharing your thoughts.
Thank you, guys.
Thank you so much. Yeah. And with that, we will now move on very quickly to the next session of the day. It is going to be on building analytical models to deliver actionable insights for storage performance optimization. The next session is going to be held by Mayuk Datta. Mayuk Datta is a distinguished technologist from Hewlett Packard Enterprise. Mayuk, over to you.
Hey, hello everybody. Am I audible? Can you hear me?
We can hear you very clearly, Mayuk.
So, I need the sharing button. It's still not enabled for me.
I think you are made the presenter. You should be able to see it now.
Okay, I'm having some trouble sharing. So just going to give me a second here. So it says I have to rejoin the session if I have to share. It's going to be a quick, just give me a quick second.
Chengappa, would you have the presentation with you?
So in fact, I see he would be rejoining. I see him dropped off. So let him.
Okay.
Yeah, let us give him a minute.
Yeah, we'll just give a minute here, and then if not, we will take it up. All right, so we will be taking up questions towards the end of the session. Each of these sessions are 30 minutes where we would, I think Mayuk's back. Hi, Mayuk. Hi, yeah, so just giving the announcement here that sessions are 30 minutes long, so you have about 20 minutes to speak and then 25 minutes, and you can have some time at the end, towards the end for questions. If you are having bandwidth troubles, maybe you could keep your video off in between, but if you're okay with bandwidth, then we'd like to see your video as well. That will help us give a, I think without any further ado, over to you, Mayuk.
Okay, so are you able to see my screen? I'm sharing. Okay.
Yes.
Okay.
Yes.
Okay. All right. Morning, everybody. My name is Bigdata, and I work for the storage division of the Hierarchical Enterprise company. I'm a software architect, a strategist, and also a data scientist. My team and I are responsible for delivering several innovations in the areas of manageability and supportability. So we work on the areas of delivering features that go into the storage management software that is used by our customers to manage the storage devices. And we also work extensively in the areas of predictive support, which is basically using AI and machine learning to predict problems even before they occur. So these are the two main areas that me and my team work on. And over the years, what me and my team has done has significantly changed the way customers experience our storage products, right? From the time they had to become experts in order to troubleshoot performance issues, to what we are offering them today are ML-driven insights and assisted troubleshooting and even recommendations to fix performance problems. So today I'm going to provide you some insights into how we have used the plethora of data that we have collected over several years from the storage devices that we have shipped that are running in the field to use the data to solve complex problems of performance optimization of storage arrays. To a storage administrator, the latency is perhaps the only criteria to baseline the performance of a storage array. Now, detecting latency issues proactively is one of the most important challenges that we storage software designers have to face on a day-to-day basis. So when we're working on customer issues, so whether it complaints of latency from some particular customer, we have to kind of look at why is it that they were not able to detect them in time, why were we not proactive about it, right? In the age of AI and machine learning, it is not a good customer experience when a customer has to initiate a complaint of a poor performance of an application running on the storage device rather than us being proactive, right? So, but the problem is that latency, whether it's good or bad, is perceived by a customer or the application user. It is not something that you could just look at the metric and figure out, okay, this is good, this is bad, because latency is subjective and it is driven by the workload that the storage device is running, right? So without a customer first complaining whether the latency is good or bad, how do we know whether the latency is good or bad? How do we proactively figure that out, right? So let's go and see how we can answer some of these business questions, right? So like I said, we have plethora of data sets, but let's see what we have right in our data set. So I would say for the last 10 to 12 years, we have not deleted a single file that we have received from the call home data that we get from the devices in the field, right? Not that everything is useful, but at least data worth the last 3 to 4 years is extremely useful in order to build this model. We ingest about records every single day, and which amounts to about 7 terabytes of compressed data per month, right? That's a lot of data. Now, one would imagine that, okay, you have a whole bunch of data. Why don't you just, grab all the data, and plot them, and you should start seeing some relationships come up. And unfortunately, this is what you will see. I mean, the pictures are in the slide. You can see what the graph on the left is IO size versus the read latency. Now you would expect that, okay, as IO size increases, the read latency would increase. But in this whole blob of data, you can't really infer, you can't even figure a directional relationship that comes out. Similarly, on the other chart is CPU busy versus latency. I mean, how busy your CPU is versus what is the latency, read latency on the storage device that you're observing. There also you see a big blob of data, right? So the issues are basically the way we cannot collect everything from the device. Right now, you are running millions and millions of IO requests every second, and you cannot capture every single IO and the life cycle of that IO that goes on. Right, so you have to capture an average. You either downsample the data, capture the data, the averages, and then you ship them. And also there are other metrics like counters versus gauges. So some metrics are like counters where they keep incrementing and they reset after a certain point in time. So if you grab the data every 5 minutes, you will get the value of the counter at that point in time. But there are some are gauges. So at the instant of your measurement, you will see a certain value, but a second ago the value may have been extremely high, and you really have no idea because you didn't poll it at that second, right? So these kind of metrics also pose a lot of challenges. So the problem with this is that also the other problem is that the storage data is sequential data, which is like a time series data. So it has clustering and temporal effects. So if you just random sample the data, that the observation at this moment of time is highly influenced by the observation that happened a minute ago, right? So it violates a lot of assumptions of classical linear regression. So it's not just easy for you to random sample and the data and just model them. But there are ways to kind of, we still have to deal with all these issues, and we kind of have different mechanisms for doing stratified sampling, sampling of the data. Like the chart on the left is something that is derived from the previous blob of data that I showed you. But here we have used some techniques of like, uniform sampling across some multiple systems. Plus we also do some bootstrapping. And after lots and lots of cleanup exercises, we still see a chart like this, right? The chart on the right-hand side is generated from our lab where we run controlled experiments. Like, for example, you run a fixed workload and you keep pumping the IOPS and you see the latency rise gradually, right? But this is like a controlled experiment. But the data that we gather from the field, that is survey data. So there's a big difference between survey data and experimental data. Experimental data, you can derive the causality by controlling the experiment, but you can't do that in survey data, right? So you can see on the left, you still see a directional relationship that the IO size, as IO size increase, you still see an increase in latency, but the graph is still noisy and you still can't use that for any sort of modeling exercise. Some of the reasons for that is also this. So if you take a look at this, there are a lot of knobs that are storage being controlled in this storage devices. Now above is a chart for a storage device with 2 controller nodes. These are the number of active host ports. So host ports are the paths from the storage device all the way to the application or to the host, right, which is running your application. You can see the number of different, there are varieties of variations in the number of host ports that comes out of just 2 node controllers. And you can see, like, majority of the devices in the field are kind of using about 20 to 25, 24 host ports. But there's a big representation also on the right-hand side. Like there are devices which are using 60 host ports, right? 60 active host ports. And there are chunks right in the middle, right around the 50, where the representation is poor. So now what we have, if we kind of, try to do some modeling here, if we take samples around that 50, if we take samples around the 50, we will hardly have any representation, right? So if I add active host ports as a feature into my model, there will not be enough variation of the data in that 50 band. So the model is going to be completely biased. Because what if that 50 has only 5 arrays and they are configured wrongly in the field, and that incorrect configuration will creep into the nuances of your model, and it will throw your model off, right? So these are the real problem that really have to deal with when you're kind of dealing with metric data, especially. So, and then we still try to kind of clean up the data and throw them into some kind of a model. Like this is a very simple we have built, and then you can see there is a directional relationship that still comes up. You can see the R score right here, hard to see. So you can see that the 0.03 is the coefficient for the active path, which says that, okay, with every step increase in your active path, you can see 0.03 millisecond increase in latency. But the problem is that even though you see a relationship here, it doesn't go with your intuition, because basically what we are saying here from the model is that, okay, you increase the number of active paths, your latency will increase, which is not what we expect, right? Because active path gives you parallelism. If your bandwidth remaining the same, if you add more active paths, you're going to see better latency, not worse latency. But that's not what you see in the data here, right? So which means that even though there's a relationship, it doesn't really go with your intuition, right? And why is that? And this is because this is survey data, it's not experimental data. Survey data would mean that, these guys, the samples that are here on the right hand side, they come from completely different set of workloads. The workloads that is running on the left hand side is completely different from the workloads that are running from the right hand side, right? And I can't even use this in a model, because I can't make a recommendation that you add more active paths and you will see more latency. That doesn't make any sense, right? Some relationships are useful. For example, this is the relationship between CPU and the read latency, and I can see a nice directional trend which agrees with my intuition. So let's go ahead and build a model on this, right? So when we build a model with that, you can see that there's a lot of cleaning that has to be done, and we kind of converted those CPU bins into categorical variables, and I can see a very simple linear model which has a 46% R square. 45% adjusted R square, and you can see the intuition here, right? So when my CPU is 11% busy, my latency will be 1 millisecond more than when the CPU was 1% busy. So this is kind of an intuition. I mean, this is something that we can work with, right? But in the storage devices, CPU is only one of the factors. There are many different factors that affect. So you can see I've taken a very small IO size bin here. The IO size bin was between 256 to 320, and in that the CPU can explain only 46% of the latency. Imagine when the IO size bin becomes bigger, this 46% latency wouldn't be sufficient for me to do any kind of inference, right? So we need to include more features. So we kind of go ahead and include like the other things like SSD saturation, IO size, and read miss. Now, this is like a starter model. This is not the model that we use in production. So just to give you an intuition of how we go about building these things, right? You can see this simple RF model, depth 3 and 150 estimators. We got a test code of 73%, and we got a pretty nice fit, right? Decent fit. And you can see the feature importance, like it says that cache miss is the most important feature that drives your latency. Next comes the IO size, and then comes the disk, and CPU is the least important feature among all the four. Now let's see how the real model in the field uses much more features. So the model that we use in production has about 70 features. It has 6 hyperparameters that were tuned using extensive grid search, right? And this is an outcome of the real model. This is from the field data. So we have the model that we have trained, and this is predicting the latency of one of the devices in the field. And you can see that the blue one is the actual latency, read latency, and the red one is the predicted. And you can see it's pretty nicely predicts the latency up to a very high precision, right? This kind of tells us that a model that was trained using the community data is able to very well explain the relationship between the latency and the features that we have used very well, right? So that's kind of like a something that we can work with. However, the problems are when we see predictions like this. And these are also the predictions that we see in the field from the same model. You can see the red line is a predicted, and this doesn't even catch up with any of the spike, right? And the reason for this could be that the latency for this device is driven by something else, not by the workload or the resources. It might be affected by network issues, or it might be a bug in the software, right? Bug in the device software. So many different reasons, right? But this is a starting for us to be able to detect anomalies, right? So if we call these an anomaly, go about scoring them. So we built a model that should have been able to predict the latency accurately with very high precision, but it did a very bad job. Now, can we use that information to give an insight to the customer that this is an anomaly and there looks like there's a problem with your configuration, or you can work with, right? But the problem is, when should we call out that anomaly, right? Whether when the latency difference is 5%, 10%, 50%, or when, right? Because that's the problem we started out with initially, right? So you can see that this is the distribution of the cutoff of the prediction errors that we have for each of these buckets. And we kind of take the 98th percentile cutoff from each of these buckets, and that becomes our threshold for calling out or detecting anomalies. But we had to go with, for this, we had to go back to modeling exercise again. So here shows, on this table, we show a lot of different models. There's a base model, and there's a Huber, the loss-based model. There's a log-all model. There's a scale-all model. And these values are very, very important. So what we show that, okay, for this model, there were only observations that have more than 90% prediction error. There are only 1.3% observations that have 50% prediction error, right? All of these, this is the best model that we choose. Because what would happen is if I use a model to do a prediction in the field, then in my training set, this model has made 0%, this has had 0% observations where the prediction error were more than 90%, right? So I could trust this model to do the right thing in the field. But in the field, if this model reports prediction errors of more than 90%, then I could call them out as an anomaly, right? So these are many, many different trial and error methods that we had to try, right? Every time we built a model, we tried it on the field data, and it worked for some, it didn't work for some. And after lots and lots of back and forth, I mean, these were the methods that were devised that eventually worked and gave us the good results, right? So the screen capture from the device management software that I was talking about, we call it SSMC. Store Serve Management Console. Store Serve is a previous name for 3-part storage array, which is now and which is also used to manage Primera arrays also. You can see that we can detect when there is an anomaly in the predicted latency in the field, and we can call them out, like these blue dots over here, calling out and indicating to the customer there's an anomaly in the latency. And we also report the top factors that possibly could be causing the latency, like host port busy, disk port busy, or enclosure port busy. So moving on, I have one more business question to follow. Do I have time to type another 10 more minutes, or should I wrap up?
Have about 7 minutes to go, but if we have any questions, we may not have time. At the moment, I don't see any questions, but
okay,
you can go ahead, yeah.
Okay. So I'll quickly touch upon the other business question, that is how much headroom is available on the array. Now, headroom assessment is a very important task for workload planning, right? And when you have mixed workloads on the array, it makes it very difficult for you to estimate what the saturation points of the array are, right? So today, typically, how headroom is measured, right? So you have different resources on the array. You have CPU, you have SSDs, you have ports, and you kind of have to look at how saturated each one of them are, and then you'll have to kind of relate them together and see, okay, my CPU is this much busy, my SSD is this much busy, my port is this much busy, and together is my array overall busy or not. But this is a very, very complex relationship for you to model, because at times you might completely saturate your CPU before you saturate your drive, right? So it might so happen. So it was very difficult conversation for our support to have with the customers in the field, because they were just asking how much busy your CPU is, how much busy your SSD is, but they're not talking a meaningful number with the customer. So it was making the performance tuning decisions and discussions very, very difficult when the field were engaging with the customers. So we had to do something about that, and that's what we came up with, a saturation model. But what basically it does is kind of takes all these CPU saturation, this saturation, port saturation, puts them together in kind of a transfer function that reports a number between 0 and 100. That's one single number, how saturated your array is. That helps you understand how much headroom your array also has. Now, this is derived based on some kind of overload factor. So arrays, when they get overloaded in the field, for example, you send in a whole bunch of writes, and the array is not able to keep up with that write, and it starts sending overload indicators and starts sending back off signals back to the host saying, okay, don't send any more data because I'm not finished, I'm not done flushing my cache, right? So those indicators served as the labels for the model that we were going to build. We took those indicators as our labels, and we started to build a model with those labels to be able to predict how close we are to the saturation point. Now remember that, okay, when the array is overloaded, it will already send an indicator. So why do we need to model to build to infer what the load point is? The model is needed to tell us that the array is going to reach a breaking point even before it actually reaches a breaking point, right? So that's the whole purpose of the model. So the problem with that was that, there were very fewer, like only 2% of the samples from the field had a load indicator. So we had to work around the problem by doing oversampling techniques to kind of fix this skew. And there were some interesting relationships that came out. So one of the examples on the left is, there is an interaction variable between the IO size, the logarithm of the IO size, and the logarithm miss. When they were interacted together, we got a nice Gaussian distribution over here. So these are the several different types of combinations that we had to try. And we had so this is a neural network based model that we built, and this is the feature importance of the model. So you have the SSD saturation being the #1 contributor to the load, likely so because it is based on the backend subsystem saturation, and then you have the CPU busy as following that, and then you have interaction terms following that, right? Using this in the model in the field, we have been able to solve very, very complex problems, such as, when there are certain housekeeping tasks that are executed by a customer. So there's an operation called tune, which converts a volume type from one type to the other type. When that happens, a lot of chunklets are moved along, a lot of data is moved around in the background, and it interfaces with those workloads. Typically, this is recommended as a customer does this operation of business hours, but we have seen from the field data that there are about 20% of examples where the customers ended up running that during the business hours, and they had seen the latency to double during these operations. So what we did is we took this ML, the model, the neural network based model that we built, we packaged it within the array, and in the array we use that to throttle these operations based on the predicted load the model estimated, right? And this is an example of this. The curve on the left hand side is without our model enabled, without the AI feature enabled on the array. When you run one of these operations, you see the latency jump. But on the right hand side, the same operation is run again, but now the AI feature is enabled, so it kind of throttles, and you can see it saves over 50% of the latency, right? Now this is an example of self-driving storage. So this is yeah, sorry.
Sorry to interrupt you. There are a couple of questions and we are almost at time, so I would like you to address them. So the first one is, what will be the impact of direct access technologies like ROCE on this sampling? That's the first question.
Okay. I didn't catch that. Would you repeat it?
Okay. Let me repeat that. That says, this question is by Santosh Paul. What will be the impact of direct access technologies like ROCE on this sampling?
So you mean when you said direct access, we were referring to the passes the cache and goes to the disk directly?
I'm not sure of that, Mayuk. This is from the Q&A section. Maybe you can just talk about what you understand, and then if there is a follow-up, I'll get back to you on that.
So, Anvit, let me try to interpret.
Yes, he says yes.
So, Anvit, this is about the Rocky based data transfer, where you could write into the memory of the server directly. So the CPU is not getting involved when the data transfer is happening.
Okay.
So like I said, right, when we started, there's a lot of resampling and filtering that we have to do on the data sets. So typically what you have to remember is, if we throw everything together in the model is not going to work, right? So like, for example, here we have done some filtering. So ideally, what I would, to your question, I would say that if we had arrays that were serving in that category of workload, we would filter that out of the model. We currently wouldn't have modeled them. So we will need to treat them as separate use cases, and we need to understand. So there's one example that I'll give you, is that what happens when your front end is super overloaded, like your front end ports, which are 8 Gbps ports, and you're driving more than 1 GB, capital GB bandwidth, right? So your front end ports are completely saturated. Your backend arrays, your SSDs and CPUs might be busy, but your backend SSDs will not be busy at all. That means the array is still overloaded, but the load indicator will not give you that. So those are the corner cases that we kind of keep out of the model. But when we have to deal with those kind of workloads, we have to take those data separately, and then we have to add new different features into the model to understand in the workload, in the ROC kind of a workload, where the typical bottlenecks are. If it's not the CPU, is it the port? If it is the disk? Right? So, and then we'll have rebuild the relationship again. So there is no one size fits all kind of a model for each and every problem. So in some of the previous latency model, we have 6 models that are rolled out. One for 2 node controllers, one for 4 controllers. For then we have the different kinds of model for different CPU sockets, servers for different sockets, and all. So we can't throw everything together in one model.
Okay, and I think one final question. This is from Ankit himself. How do you model for some background processes that might run inadvertently, like SSD trim or garbage collections that can't really be planned or postponed?
Yeah, so we are actually doing them in phases. So in the current release, we have taken up RAID rebuild. So first release was about tune operations. Second release, we have taken up RAID rebuild, and we have also taken up the garbage collection. So what really happens is that these tasks that run, these tasks will first query our engine. So we call that AI engine autonome. So that task will first query autonome to give it back the load indicator, and the task will automatically throttle itself based on what the predicted load of the array is going to be. So the garbage collection code, the garbage collection thread is going to ask autonome, okay, give me what your predicted load is for the next 5 to 10 minutes, and based on that, it is going to decide whether it's going to run now, or is going to collect aggressively, or is going to throttle itself. So the onus is on the task to do this, not the other way around. So autonome would not figure out, okay, what else is going to run and adjust itself. It just gives a recommendation of a predicted score.
Right, I believe those are the questions we have. Maybe you can wrap up your final thoughts, and we can just
the final thought I want to say that this is the first instance of self-driving storage, right? We have been talking about AI-driven storage, self-driving storage. So this was the first offering that we have from HPE in that space, self-driving storage. This was released 6 months ago, and it has made quite a news since then. If you want more information, so here are some of the materials that you can go. There are YouTube videos that shows you how to do some of these features. And that's all I had. Thank you.
Thank you so much, Mayuk. That was a very informative session indeed. And I believe if there are any more questions, we will definitely connect them with you directly so that they can get them clarified. This is your virtual memento. Thank you for being with us here at IEEE Data and Storage Summit 2020. And it was a pleasure having you on.
Thank you. Same here.
All right, with that, it's time now for our next session. This is a session on technology trends in secondary storage systems. The session is going to be conducted by Asaf Natanzon, VP of Technology, Huawei Storage, Israel. Remember, this session is 30 minutes long. We have 20 minutes for speaking, and about the last 5 to 10 minutes we could have for questions and answers, if any. Over to you, Asaf.
Hello, can you hear me?
Yes, I can hear you, and I can see you as well. Nice to see you.
Wait, I don't see I need to share the presentation, or you're sharing?
Yes, you are presenter, so you can if you want to.
Oh.
All right, I think we can see your presentation as well.
Okay, so hello everybody. My name is Dr. Asaf Natanzon. I'm Technical VP at Huawei Storage. And today I'm going to talk about the technology trends and how they're affecting secondary storage solutions. So a little bit about the agenda. So first I'll introduce what secondary storage is and why is it happening today. Then I'll describe some challenges that we see in this realm of secondary storage, and later some core requirements and how to build what we need to build the best secondary storage. Let's look at first at the evolution of data lifecycle management and data reuse. So basically today we have a lot of products that actually handle with data management, starting from simple storage to store the data, moving to services which are typically storage services like disaster recovery and high availability, but also of course the traditional backup with the compliance required around it, archiving to cloud. Not new, but something that was born with the evolution of cloud, Copy data management that appeared due to the huge amount of copies of data that we have. As without accessing the data fast and understanding where our data is, classifying the data for understanding which data is sensitive and understanding how to comply with governance rules like GDPR, security of the data, ransomware detection, and other things of the data, and of course analytics with AI now being important to get value from the data. So running analytics on our data is also becoming critical. Now we have a lot of products in all of these areas, but secondary storage is saying that all of these abilities of managing the data can come from a single product. The pioneers in this area were already 6 to 7 years in the market, basically trying to consolidating all the data management silos into a single solution. This is possible also due to a lot of technology changes like SSDs and the disaggregated architecture and hyperconverged architecture. And I think that this is evolving very fast. Looking at this survey from Wikibon that shows what are the plans of companies regarding adoption and increasing of usage of products. As you can see, Rubrik and Cohesity are leaders in this area, while on traditional storages and databases, there is actually a decline in investment. This secondary storage is a very, very good place to be in today. Life data management. So basically, we need to manage the data everywhere. We need to manage the data on-premise, in the cloud, and over the edge. We need to give all type of data services like tagging the data, searching, cleaning, minimize duplicates of data, reducing the data footprint, migrating data from place to place, tiering data to save money, and also discovering what we have. We can look at this as like 3 tiers of the data. First, we need to store the data. This is like primary storage abilities, but then we also need to protect the data, backup for compliance and for being able to restore, archiving the data, having a disaster recovery, detecting which part of the data are vulnerable, being able to detect and avoid the ransomware, being able to sanitize and clean the data, both for giving it for test and dev use cases, but also if we want to keep the data in cloud and need to comply with GDPR, for example, and also being able to classify the data into pieces. And of course, the top layer is actually getting value from the data, starting from test and dev use cases where customers want to actually develop the application and get more value from it and need to run the data for test and dev. And also all the AI and analytics use cases that we see today, trying to get more value and more money from the data that we already collected. Let us look a little bit about the challenges in this area. So first, I'll start with the test and dev use case. So what is this use case? So basically, you have copies of your data and your developers want to develop new features, and they need to be able to access the data in order to be able to do the development. Now, in order to access the data, you cannot let your developers see, for example, credit card numbers and personal information about your customers. So you need to anonymize the data, and then you need to let them access the data and be able to run it. Now, typically in traditional systems, these were 2 silos. There is the backup silo, and from the backup, usually you took a copy, you sanitize it, you keep it in another primary storage, and then let the user access it. Obviously, this is a very tedious and very expensive process. First of all, you need to double the storage. Second, you need to move the data and do the anonymization. All of this process took hours to days and was very. And now the fact that the secondary storage are available today that allow you not only to back up the data, but also to access the data with decent performance allows to actually merge the use case of test and dev into the same use cases as backing up the data and storing the data. So the benefits are very, very clear. You can access your data instantly. There is no disruption and risk to the production. You save a lot of capacity because you keep your backups and use them. The challenges are that now your backup appliance cannot be just for backup. Typically, backup appliances like data domains were very much optimized for the backup workload, but not for random IO workload. And basically, this is not good enough for test and dev. So we need the new hardware and new algorithms to allow accessing the data in a near primary storage performance. But still, we need to keep the data in a very, very efficient format because, again, this is a backup data and we have a lot of copies. Another requirement is also data anonymization, which needs to be integrated into the product, whether it's real-time anonymization that allows you to access the anonymized data without actually changing the data stored, or we need an efficient way to keep the anonymized data inside the secondary. But typically, anonymization will harm deduplication severely, so there is a need to do something smart here. Looking into anonymization, which is one of the key requirements for letting user access the data in a test and dev environment. So we can look at the two types of data. There is the unstructured data, which include text and documents and images and videos and audio files. And for these, when you let them access, you need, for example, to remove sensitive data in free text, like credit card numbers, personal data. For images, you may want, for example, to hide all faces or only to hide the faces of children due to local rules about privacy and anonymity. Also in audio files, you may want to remove the ability to recognize the individual speaking, so you may need to replace the voice print. Looking into structured data, so database tables, again, you need to remove some of the fields like credit card numbers, maybe names, addresses. The main challenge here is how to do it, first of all, fast, seamless, how to do it when you move the data correctly. So for example, if you move the data to a cloud and the cloud is outside of your country, you may need to do some anonymization in order to be able to keep the data in this area, because it's illegal to keep personal data outside of your country. But also there is a challenge here about storage and efficiency, because if you mask the data, some algorithms like deduplication will work very, very badly. So this is also a requirement on how to actually keep deduplication at the same levels while keeping the data also in anonymized copies. Looking at the data, basically we have one of the big challenges of secondary storage and data management is the vast amounts of data. So we have data running on the edges, on-prem, in the cloud. We have structured and unstructured data, and the data is growing exponentially. If we don't have a smart way to locate and access the data, there is no way to manage such billions of entries, millions of data sources. It will be impossible. And obviously, we see everywhere that there are catalogs. If it's in secondary storage arrays like Rubrik and Chronicity catalogs that allows you to search inside your backup copies. And if it's in primary storage like EMC Isilon, you have catalog that allows you to access the data in real time, understand what files you have, do tiering for the data, understand if you have duplicate files, also do some auditing, understand who is changing and deleting files, so that if there is a rogue employee, you'll be able to detect it. Overall, I think catalogs of the data are going to be more and more important and more general in the way that they are going to cover all the aspects of the data center, and not just the catalog for secondary storage or a catalog for primary storage. There is a need for a global catalog that will manage all your assets on-prem, on the edge, and in the cloud. And I think we're going to see a lot of advancements in this area in the following years. Data reduction. So in backup scenario, I think data reduction is very obvious. Data reduction and deduplication is what enabled moving from tape to disks. There are several traditional techniques like variable length deduplication, which typically used by backup solutions because it has some impact on random IOs. We have fixed size deduplication, which is used today by almost all flash arrays because it allows to do data reduction while keeping very low latency and response time. And of course, delta compression, which is used by both backup solutions and primary storage solutions. If you're looking at secondary storage, I think we need to take it to the next level. Secondary storage poses us some new challenges because on one hand, we are handling backup copies, so we need a very efficient deduplication. But on the other hand, we need random access to the data because of the test and dev areas. So I think that there is a need to actually improve and reinvent some of the data reduction techniques so that we will get the best of both worlds, so that we'll get maybe deduplication almost as good as backup appliances and performance almost as good as primary storage, but not so we need to reinvent here. Another opportunity in secondary storage scenarios is application-aware compression and deduplication for images, genomic data, databases. Also, when we're speaking about anonymization, there is a need maybe to create algorithms that allow you to keep anonymized copies of the data, but in a very efficient way that is aware of the original data and that will allow you to have the best data reduction. Because typically, if you anonymize only some of you look at the database, if you will anonymize only some of the portions of the table, in many cases, you will get a much worse deduplication and compression. Looking at cloud is a very important use case in all the backup realm and secondary storage realm. The original thoughts about going to the cloud were about saving money. You can tier the data to an S3 for backup or just for tiering and save money, especially if you don't have a second site. Then keeping the data in a different site is not possible for you, and keeping it in the cloud allow you to keep it in different site to maintain much more availability. Disaster recovery in the cloud is even more important here because it enables like small offices and small businesses that couldn't have a second site and don't even have them, and even if they have the second site, they don't have enough money to build the same hardware as they have in on-prem. In the cloud, the value is that you can get the hardware on demand, so you can keep the data, for example, in S3, and do the disaster recovery and bring up all the assets and all the CPUs and virtual machines only when you have the disaster. So the cost for the DR is just when you're doing the DR and not continuously. Test and dev is also an enablement in the cloud because in test and dev and analytic scenarios, sometimes you need like different hardware and stronger hardware for a short period of time, and the cloud enable you this. But one of the challenges will be that you need to, in the cloud, you cannot keep always the data as it is, and you need to do anonymization either when you send the data to the cloud or on the fly. And this also leads to many innovations about how to keep the data anonymized in the cloud and not non-anonymized on-prem and many other things. Also, to move the data from the on-prem to the cloud and back. The challenges are the usual suspects. Bandwidth is very expensive, so moving the data to the cloud is typically very expensive. Storage costs in the cloud and managing the cost in the cloud is very complex. And for this, I think, first of all, we need like super source-based deduplication algorithms and also AI-based management for the costs and understanding where to put the data and when to put the data and calculate all the costs. We saw that NetApp acquired Spot to understand the costs of the data. I think in secondary storage scenarios, this is also critically important because at the end, the user wants to get some SLA. He doesn't care where the data sits as long as he has the availability and he gets all the value that he had. But then calculating the costs becomes almost impossible. Another topic in the cloud is how to protect native workloads. So cloud native workloads like Kubernetes, function as a service, all the cloud databases are actually already in production in many businesses. And it is, of course, to be able to protect this data and leverage it in the most simple way to be on par with traditional workloads. And actually, in the recent couple of months, we've seen a lot of acquisition in this area, like provokers being bought by Pure Storage and Kasten being bought by Vim because they want to provide a backup for Kubernetes workload. But I think that in the future, even in the near future, we're going to see like many more use cases, because the fact that how these cloud native applications are built, you can actually leverage and get more from the application. You can be able to detect applications automatically due to the YAML files in a much more easier way than traditional applications. You can integrate the test and dev with your CI tools and automatically open debuggers when you with the correct image of the data when there is a bug and send a notification to the user. A lot of things can be done here that are not possible with traditional workloads, and I think that soon we're going to see the next step in data management for such applications. Last area I will discuss in the challenges is the edge computing. Obviously, there are many edges in the challenges on the edge, like huge number of devices. We're talking about millions of devices that need to be managed, limited bandwidth from the edge to the core, and limited compute resources on the edge, so we cannot do all the calculation on the edge. So at the end, we have critical requirements of understanding how we understand which data to collect centrally. How do we move the data? So we need things like source-based deduplication and being able to send the data to maybe non-trusted area, but still maintain deduplication. And obviously, over all this, we need a catalog, because you cannot manage millions of objects without abilities to search them easily, like in a Google-like search. So I think this is also like one of the big challenges that are happening in secondary storage. Looking at all the challenges, I think this leads us to the requirements of a secondary storage solution. And I see three main requirements here in the secondary storage. The first one is simplicity. We are managing increasing amounts of data, and in order to manage them, we need to keep everything as simple as possible. Without simplicity, it will be impossible to manage. Second, we need to leverage all the other changes that are happening to be able to deliver a cost-effective solution. There is no one solution that fits all, and this is why we need all the new trends in the hardware to allow to build customized solutions for the customers. And last but not least, AI needs to be everywhere, both for achieving the simplicity and both to selecting and understanding which hardware to use and optimally use the hardware. Looking at simplicity, due to the fact that secondary storage needs to manage almost infinite amounts of data, and it allows users to use many technologies, the architecture has to be inherently simple. It has to be deployed simply, it has to scale simply. So this is why we saw that the successful secondary storage are all of them are scale-out architecture. The system needs to be managed autonomously by policy, and not a policy. If it's a single click per workload, it's already too much, because if you have millions of edge devices, you cannot even do a single click per edge device. You need the policies to be managed automatically, and that the system will just let you select when it has some doubts. They are also critical for the simplicity. Without being able to Google search and understand based on analytics what are the problems and what you need to do, it will be impossible to manage such huge amounts of data. Looking at the hardware again, I think that the use cases are so wide that you cannot have one hardware that fits them all. And I think the new trends that are covered very well in this conference are going to be very important, because if we look at the extreme cases that we have here, so Some user will just want more like backups or archive solution, and they will definitely need much more spindle than SSDs. Others will want to do more test and dev, so they will need to increase the amount of SSDs they have, because if they access the data from hard disk, it will not be fast enough. And then there are the ones that are focused on analytics and AI over the data, and they will need much more specialized CPUs and GPUs and the TPUs for getting the data. So depending on how you want to use the data, maybe you need quite different hardware. And this is why I think that scale out disaggregated architectures as opposed to HCI are very important as the future of secondary storage, and also looking into composable hardware. So if the user will want more analytics, he will put on the memory fabric some GPUs that will be able to do some AI on the data, or if you want more SSD or faster storage, maybe we'll put some SCM storage node on the bus, and we'll be able to increase the performance. We need all the system to be very, very dynamic and leverage all the storage technologies to allow from very cheap machines for just the backup and archive use case to much more expensive machines, probably for the use cases of analytics. Last but not least, like I said, it's AI. AI has to be everywhere to help us generate policies and detect human errors, to predict failures and maybe restore data before an error occurred, so that the data will be ready even before the user knows that there is a problem. Optimizing all the workload, understanding where to put the data, how to leverage the cloud, how to minimize the costs, which hardware to choose, for example. So if you start using the data for different purposes, recommend what type of hardware you need to add to your system in order to get it running faster and better. And obviously the catalog that needs to support simplified analytics and allowing you to detect anomalies in a very fast way. That's all what I had to say. Just few closing remarks. So in Huawei, we are looking into secondary storage, and we think that all these trends are important, and that this is a key part of the future of storage and how you can leverage your data. So I think that all of these trends are happening today. All
right, Asaf, we have a question. How do you see smart cataloging with AI learning working along with security, rights, and permissions? Since the inferences might turn out to be different based on what data set is accessible and what is not.
So obviously you cannot run, so there has to be some right management. If you don't have access to the data, you will not be able to learn it. There are also a lot of techniques that allows you actually to run analytics on already anonymized or hidden data. This is also definitely part of what secondary storage needs to do in the future. There are a lot of activities in startup today that allow you to run AI workloads on encrypted data, for example, and this is also should be part of the secondary storage, obviously. So I covered a lot of the trends happening. This is definitely another one that is happening. We see it in many startups, and I think that also the enterprises are going to leverage these technologies soon.
All right. I believe we are on time, and I don't see any more questions, but if we do get any more, we will be passing them on to you. Thank you for your session on trends in secondary storage, Asaf. That was really informative. And here's your virtual memento. Thank you for being with us here at IEEE Data and Share Summit.
Thank you.
All right, yeah. And with that, it's time now for our next speaker to come on your screens, and that is going to be Mr. Saurav Bansal. Saurav Bansal is the Associate Professor at IIT D. He is going to speak on compiler AI, reimagining the compilation infrastructure. Over to you, Saurav. Saurabh, I believe you're on mute. Ah, yes, yes. I can hear you.
Great. Great. Wonderful. I'll just share my screen.
Sure.
All right. Can you see my screen?
Just a moment. I believe you're sharing it. It says yes, we can see your screen.
And you can see my first slide, which says compiler.ai.
Compiler AI reimagination, the compilations or also, yes,
Great.
yes.
Okay, thank you. So thank you for having me here. I was just looking at the list of attendees. It seems like a large list of attendees, lots of Indian names, and I also noticed some of my colleagues from IIEEE Bangalore and other IITs, and also lots of people from Hawaii. So hello to everybody. It's great to meet you virtually, and I'm looking forward to the talks. I've enjoyed the talk so far. All right, so let's get on with my talk. I'm talking about compilers, or I call it compiler.ai, and I call it reimagining the compilation infrastructure. This talk is, slightly maybe not something that we've been hearing since the morning, and maybe not something that we'll hear in the rest of the conference, but I still hope that it's going to be relevant and interesting to the audience. So as we all know, what is a compiler? A compiler takes a program source code and generates an executable code that runs on. Okay, and so by the way, if you have any discussion items, questions, feel free to interrupt me. I'd rather interact and understand the questions and the concerns that people have rather than just keep speaking. I have my own talk, but that's fine. All right. So the problem is that the hardware complexity has been increasing drastically. This is true both for the microarchitecture instruction set architecture. Complex instruction sets have been introduced over the last decade, really complex instruction sets. And the reason for this is primarily because there's saturation in CPU speed. There's also, an impending saturation in the Moore's law. And so you need more and more innovation at the architecture level to be able to get the most juice out of the silicon. And so the only way you can do it is basically you expose more complex abstractions to your software. And now it's the job of the software to use these abstractions. Now, while I'm talking about this in the context of hardware, microarchitecture, ISA, which is instruction set architecture, is also true for storage systems, right? So there are more complex memory hierarchies. There's persistent memory, there is NVRAM, there is, there are all kinds of diverse hardware substrates, and you need to be able to optimize for them. And that's what most of the, let's say, the storage companies are kind of spending most of their effort in, manual optimization of stuff. Now, hardware complexity is increasing, but hardware complexity, as I noticed a question, maybe that was not for me. So hardware complexity has been increasing, but the other thing is that as a result, compiler complexity has been increasing drastically as well. Now, even in the context of, let's say, storage or databases, for example, people basically, sometimes they do all the optimizations manually, which means they're doing everything. Let's say they're writing C++ code or something like that. That I would call that manual optimization. Or they are using high-level languages. For example, SQL is a high-level language for databases, and then they write query optimizers to basically optimize for them for the hardware substrate. And so these optimization logic keeps increasing, keeps becoming more and more complex over time. And the other problem here is that the programming languages are becoming more and more advanced. What do I mean by advanced programming languages? Well, they're becoming higher and higher level, right? People don't want to code each and every nitty-gritty of how things are moving. People design higher level abstractions, and then it's easier for the developers to develop for these high level abstractions. And so what happens is that the gap between the programming languages and the hardware substrate increases. And that means there's more tension on the compiler side. The compiler is not doing a good job. You're not getting good performance. And so the demands on the compiler are increasing over time significantly. Traditionally we think of compilers as GCCs, compiling C to assembly or something like that. But compilation is not just GCC, it's actually all across the spectrum. I just wanted to make that point. So here's some data on compiler complexity that'll give you some clear idea of why I say compiler complexity is increasing over time. So this is the number of source lines of code into 1,000. all right? So source lines of code of GCC, all right? From 1988 to, let's say, last year, 2019, okay? And in 1988, the size of GCC was, let's say, around 20,000 lines of code or something like that. Today, it is over 16 million lines of code. And the other interesting thing to note here is that it has been linearly increasing over time. The reason it's been linearly increasing is basically because as humans, we cannot be increasing at exponential rates. I mean, you only get a small number of developers to work on these kind of complex software, and they keep doing as much better job as possible. But what this graph is showing you is that there is so much, there's so much to be done, and we are just kind of doing things over time. But it just indicates that there's probably so much more to be done that has not yet been achieved, and that's very, very true, as we know from what the compiler produces versus what would have been the best possible thing that would have been produced. All right, so we discussed that GCC has over 16 million lines of code. And so for what it's worth, people have been talking about compilers in all different kind of fora, in all different kind of fields. So for example, I found this interesting article that was not really totally technical, but more like visionary. And they said compiler top minds in machine learning predict where AI is going. So AI being a very hot topic, I picked on this one and says, I expect an explosion in the importance and adoption of tools like PyTorch, JIT compiler, and neural network hardware accelerators like GLOW, right? So compilers are kind of at the, you have things like TensorFlow. There's a lot of work going on at optimizing the compiler for TensorFlow. Now, I should point out that, it may seem like GCC and TensorFlow compiler are totally different beasts. And why am I kind of conflating them into one? But the basic principles remain the same. The basic architecture of GCC and TensorFlow's compiler is pretty much the same, just that the level of abstraction has been raised a little bit. So if we can make improvements in any of these space, fundamental improvements, it impacts the entire spectrum. All right, so what are the implications of the complexity of a compiler? So we now understand that compilers have complex, but what are the implications? First of all, compilers have software bugs. It is well-known fact, researchers are year after year churning out bugs in compilers, and that's a very worrying fact. Imagine if you are sitting in a self-driving car, and the code for that self-driving car was compiled using GCC, and it so turns out that you have made very careful, the engineers were very careful about the source code, but the compiler had a bug, and because of that, would you be comfortable sitting in such a car, right? So that's a very problematic issue. And the other thing is, you have the possibility of security exploits through the compiler, and this is also a very well-known thing. People exploit bugs in the compiler, which usually people overlook, and hackers exploit. The other bigger problem, I would say, is that the optimization is insufficient. I mean, the optimization that we have for today's compilers is huge distance away from what is the best possible thing. It's not even close. And the reason that we are not being able to get the entire optimization potential of a compiler is because compilers are so big and unwieldy that development pace is very slow, as we have also seen using the GCC graph. And only highly specialized programmers with decades of experience can participate. And that's another problem. There are only very few people, very few specialized expert programmers know this art, this black art of doing compiler development, and that's a big problem. All right, so I'm going to talk. So I've kind of set the stage in terms of what is the problem and stuff like that. I'm going to talk about what is the research that we have done and we are doing in this space. This is the space that is that I work in. I'm going to talk. I'm going to talk mostly in the context of compilers like GCC and LLVM, which is compiling from C to assembly. But the same constructs basically abstract out to things like storage systems or databases or any other complex system where you need to have a easy programming model for the human programmer and a complex computing substrate. In fact, I should point out that we have been in talks with the Huawei to do some kind of programming model and compilation support for persistent memory. So so you can imagine that there are some kind of synergies there. All right. So the first thing is to deal with this problem that compilers have software bugs. we basically have we are developing a tool which automatically generates proofs of correctness of compilation. All right. Sorry. So what do I mean by proofs of correctness of compilation? Well, these are this comes in the domain of formal methods. So there are lots of tools that are being developed in formal methods, and one of the tools and that our research group is developing is that it basically checks the result of the compilation against the source code. And the correctness guarantees of this check are much, much stronger than the correctness guarantees of what the compiler is giving you, right? So if that check passes, then with a very, very high probability, you can be sure that the compilation didn't have any bugs. And so now you can be comfortable sitting in the car whose code was compiled using this compiler. All right. And this gives you end-to-end safety and security guarantees for the software toolchain. This is one part of our research. The other problem, which is optimization is insufficient. So we are developing AI algorithms and a system to automatically develop optimizations. In this architecture, machines identify optimizations and the compiler becomes smarter over time. So unlike the current development model of compilers, which is predominantly manual, everybody has to codify the transformations, the optimizations manually, and that is the reason that the complexity has been growing. Things are slower than what we want. Can we get machines to do this for us? And instead of we doing all the optimizations manually, we just identify algorithms that allow the machines to automatically learn these optimizations automatically. In that way, that would, if this can be done, that would be awesome, because we would have really made a disruption in the space of compilation. Okay, so the first part of this is called a translation validator, and my talk also is structured similarly. I'm going to talk about a translation validator. It's we have a very mature translation validator, and we have some papers to show the results and stuff like that, published papers at top conferences. So I'm going to talk about our results, the problem and the results a little bit. Then I'm also going to talk about our super optimizer. Here, it's very much work in progress, but I'm going to share a glimpse of one published work that we recently published in this space. All right. So yeah, so before I talk, let me just tell you what to expect from my talk. In the translation validation space, we have the first robust black box translation validator from C language to x86 assembly. All right. Now, once again, while we are doing it in this context of C to x86, this can be generalized to any other translation as well. Why did we choose C to x86? Well, it turns out that the compilation support for the C language to assembly is the most advanced compilation support today in terms of the optimization it supports, right? Just because the number of viewers or the audience for C language, performance critical C programs is huge. And that's why there's much more focus. So for example, if you take a language like Java or Python, you would find that the optimization support for these languages is so much weaker than the optimization support for languages like C. And so if we want to test our stuff, the most difficult target is the C programming language translation, and that's why we are looking there. Because if we can do C, we should be able to do other things as well. Our translation validator gives strong guarantees on the result of a compilation. My second part of the talk is, so in terms of super optimizer, we have developed a people super optimizer for x86. If this doesn't make sense, it's okay. I'm not going to really talk about it, but I just want to mention it. We have a binary translator from PowerPC to x86 that's also based on super optimization techniques, automatically learned translations rather than manually codified translations. And work in progress, we are doing a code generator from LLVM IR to x86. In the super optimizer space, I'm not going to talk about any of these things because two of these are a little bit old and maybe it's too late to talk about these works in this conference. Third one, we are still working, so I'm not, it's not right to talk about it right now, but I'm going to talk about something related that we have recently done and published. Okay, let me start with talking about the translation validator that we have done, and here is a motivating example. So consider this program, the familiar strlen function in C, and I'm sure most of you must have used this function in your code. This function basically takes a pointer to a character. Actually, this is supposed to be, I hope, this is expected to be a null pointed array, null terminated array of characters, or in other words, a C string, S, and it returns the length of that C string. And the way it works is very simple. I mean, the logic in a simple C program is the following, that you just initialize an iterator variable P to the start S, and then you keep iterating P until you encounter a null character. The moment you encounter a null character, you break out of the loop and you return P minus S. That would represent the length of the string. Now, this looks very simple, very easy to read. I hope everybody could follow this logic and say that, okay, yeah, indeed, this is the str. This is how strlen should be implemented. But how is strlen implemented in practice? Is this how strlen is implemented in your libraries? No. So the right-hand side shows the glibc version of the same function strlen. And if you try to read this function, I can promise you that you will find it very difficult to read it. Let's try to do it just to kind of set the stage. So here the signature of the function is the same, but now we have a pointer and a long word pointer. Then we have these temporary storage, long word, high magic, low magic, and then we have this loop which says, you increment PTR until PTR is until the next 8-byte boundary, until the next 8-byte alignment. And if you find a null character anywhere in the first 7 bytes, 7 or less bytes till the next 8-byte alignment, then you are done. Otherwise, you use the more optimized vectorized version for this implementation. And the way the vectorized version works is that you basically read 64 bits at a time. So that's what ulong stands for. And then you do something. It's pretty complicated. And if I try to explain it, I'm going to run out of time to try to explain it. Now this is the actual implementation of strlen in glibc. And this is just this is just an example to show that simple interface, complex implementation. That's what a storage system is also, right? I mean, simple interface, just get and set. That's it. But complex implementation because of all the optimizations going on, right? And so now the question is, how do I know whether these two programs are equivalent or not? It's very, very likely that I could have made a mistake while I'm coding this up. Of course, lots of people must have reviewed this, but there should be an easy way for a normal mere mortal like me to basically be able to see that this is correct. And that's what a translation validator will be able to do. It's going to be able to say, indeed, these two programs are equivalent. And if it says it's equivalent, you can be completely careful, right? So that's it. All right, so how does a translation validator work? Well, think about, so here is one way to do it. Let's say there's one program A, there's another program B. Program A, both of them, let's say, have a single loop. I'm taking a simplified example. Usually programs have lots of loops, but loops are the biggest problem, by the way. And they have some conditions, they have some body. Let's say the first one has body A, second one has body B. The first one returns some value A, the second one returns some value B. How do I check whether these two programs are equivalent? Well, the way to do it is probably I will construct a product program where I execute both programs. And then I say, is it true that the return values are equivalent? But I want to do this for all possible inputs, right? So for all possible inputs, it's not just okay to do it for one input. And to be able to do it for all possible inputs is impossible because the number of inputs is almost infinite. And so the way to do it is basically somehow if I'm able to summarize the first loop and if I'm able to summarize the second loop, what it's doing, then if I have some kind of theorem prover that says, by the way, this is what the first loop is going to do. Maybe it computes the first Fibonacci number, it computes the nth Fibonacci number. And the second loop is also computing the nth Fibonacci number. And then I've summarized the loops and I say, okay, both are computing the nth Fibonacci number, they are equivalent. But that would be really difficult to do. How do I know what is this program doing? That's an undecidable problem. So a better approach is basically that somehow I'm able to correlate the some portion of the first program to some portion of the other program. So let's say, one iteration of the first program which executes A I'm able to correlate with one iteration of the other program. And if I'm able to do that, and after one iteration, I'm able to relate the states of the two programs using this red line, then I have made some progress. And if I can do that for every iteration, I can say, after every one iteration, if I just execute both these programs in lockstep, so A moves, then B moves, then A moves, then B moves. Now that would be a better, and then I'm able to give an invariant that, by the way, if this is how the programs execute in lockstep, then I can relate the states of the two programs using an invariant, and the invariant also has to be guessed and inferred. So this is an easier way of constructing a product program. I say I execute A and B in tandem rather than executing all of A's before all of B's. And then I also kind of infer an invariant. And now if I want to check whether these two are equivalent, what do I need to do? I need to use a theorem prover to say that the invariant is true for the first time I enter the loop. The invariant is true. This is the inductive step that, if the invariant is true in the previous iteration, it's going to be true for the next iteration. And finally, I want to show that if the invariant is true and I exit the loop, then I am sure that the return values will be equivalent. And this is a much more tractable thing to do rather than basically trying to summarize the loop. I'm basically being able to correlate the transitions. This is possible for equivalent programs. It's not always possible for all equivalent programs. And the question is, can you do this automatically? I mean, manually also you will require a lot of time. Can computers do this automatically? And that's where, by the way, I want to point out that the problem is more difficult. How do I know whether I need to correlate one iteration of the first program with the other iteration, or two iterations, or three iterations, and so on? So for example, here's an example which correlates two iterations of the first program with one iteration of the second program. And in which case my product program would look something like this. It will execute A twice and then B, and only then I would have the required invariant, and then I would be able to prove equivalence. So the problem is, so I guess I hope I have motivated the problem, and the problem is how to identify these correlations between snippets of one program and snippets of another program, such that the required invariance can be automatically found to prove equivalence. Now there are two parts: how to identify these correlations and how to identify the required invariance. There's been a lot of prior work on how to identify required invariance. Our contribution is in the blue. We gave an algorithm to identify these correlations automatically using a counter examples guided best first search algorithm. I'm not going to go into detail how this works. I just kind of telling you, giving you a flavor. It's the first equivalence checker to compute equivalence across aggressively unrolled vectorized code involving multiple complex loop transformations. And all this is done statically without running the programs even once. Okay. All right, so this was our paper that was published at UPSLA 2020. This is joint work with two PhD students at IIT Delhi, Shubhani Gupta and Abhishek Rose. And just to complete the discussion, this particular example, our equivalence checker can handle very easily. In fact, in our paper, we show much more complicated examples that our equivalence checker can compute equivalence for. And I should point out that while we are doing this equivalence for C programs and x86 assembly programs, the same ideas can be applied to larger, high-level abstractions and high-level programs as well. I'm going to move to the next part of my talk, which is super optimizer. The work on people super optimizers and binary translation is kind of old work from our group, and current ongoing work is this. But today I'm going to talk about this particular work that was published at PLDI 2020. This work is titled Ooh La La, Order of Evaluation Based Alias Analysis for Compiler Optimization. This work is a direct result of our efforts to develop a super optimizer. And so this is a complete work, published work at a top conference. So I'm going to talk about this. So what is order of evaluation based alias analysis? All right, this is the key word, order of evaluation based alias analysis. Firstly, what is order of evaluation? Okay, so consider this particular program. And can you tell me what should be the output of this program? It initializes A to 0. This is C. I'm assuming this is C. And I initialize A to 0. And then I say printf. And then I want to print A equals 1 plus A. By the way, this is a legal expression in the sense of syntax. A equals 1 is going to return value 1. It's going to assign 1 to A and also give you a value 1. And then you want to plus A. Now the question is, should I first assign and then add, or should I first add and then assign, right? I mean, that's the confusion here. And that's why I ask you what should be the output. And so the C language says that it's actually unspecified. You can do it in either order. You can either do assignment first and then addition, or you can do the addition first and then add. And the answers will be different. So what should be the output? And can there be multiple outputs? And can different compilers produce different output? In fact, it turns out that different compilers produce different output for this program. But the real answer, as per the C standard, is that this program is illegal, because what it's basically doing is it's trying to assign to the same memory location and read from the same memory location in such a way that the relative orders are unspecified. And this is exactly the notion of a race condition, except that it's not on multiple threads. Within a single thread, this is a race condition. All right, and a race condition is undefined behavior in C, which means this program would be illegal when it executes because it's trying to read and write to the same memory location such that the relative order is unspecified because they can be executing anytime with respect to each other. So, all right, so what about this program? It says star P equals 0, star Q equals 0, and printf star P equals 1 plus star Q. The only thing that I've done is I've replaced A with star P in one place and star Q in the other place from the previous slide. And the answer is this program would be legal only if star P and star Q cannot alias. If star P and star Q are aliasing, then we have the same problem and we'll get again the race condition and the undefined behavior. So this program is legal only if star P and star Q cannot alias. All right. So that's interesting because now this program is legal only for some values of P and Q. It's not completely legal, but it's not completely legal either. It's only legal if P and Q are not aliased in any execution. So this gives us an idea for compiler optimization, and this is the optimization based on this. And so let me ask you this question. Let's say there is this program in C which says for I equals 0 to n, bj plus equals ai. Is it possible to transform this program? Notice that in this particular program, there are 2 memory accesses. In fact, there are 3 memory accesses in every iteration of the loop. You read twice and you write once. You write to bj. And you read twice. You read from both ai and bj. Can I change this program such that I register allocate bj and I just add to R the register and then I finally add assign to bj? Can I do this? The answer is no. Okay, because AI and bj could have aliased, in which case these 2 programs won't be equivalent. All right, if AI is equal to, if the address of AI is equal to the address of bj, then these programs are not equivalent, or could be equal. In any iteration, if they could be equal, then these programs are not equal. And so this is an important consideration in compiler optimizations. And these are called aliasing queries within the compiler. The compiler wants to know, can star P for some P and star Q for some Q alias, which means can they point to the same location? And the possible responses can be definitely not, definitely yes, can't say. And definitely not, basically, in the previous example would be great because then I would be able to register allocate and save 2 memory accesses and make, actually that would give me a 3x performance improvement, right? Almost. And definitely yes. So also I have to think can't say is a very bad answer because it's almost like saying I can't say, right? So, and most of the time the compiler is basically saying getting the answer can't say, and so it's being conservative in the optimizations that we perform. And conservative optimization skill performance. So here is an example: star min equals star max equals 0. So here's a program that tries to compute the index of the array which has the smallest element and the largest element. All right. So the question is, can you make this? Can you vectorize this loop? And the answer is no, because we don't know whether whether min and max could be pointing to the same location or not. Right. So that's the short answer. I don't, I'm not going into full details, but if min and max can alias, then I can't vectorize. If min and max cannot alias, then I can. And it turns out that using the semantics of C, the order of evaluation semantics, if I look at this particular expression, star min equals star max equals 0, I'm trying to write to 2 different locations, min and max, simultaneously. And this would be illegal by the same argument that I had in the previous slide if min and max were pointing to the same thing. That means I can assume that min and max do not point to the same thing. And if I assume that, then voila, I have been able to vectorize my code. And in that particular example, I get around 3.5x speed up for that program. Here's a real example from the Image Magic benchmark in spec. It's an image manipulation program. And this is the code that the developer has written. It turns out that if we are able, now this, here there are lots of pointer dereferences, right? You see pointer, 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 and then there's array dereference and so on. And the compiler has to make conservative assumptions, and based on that, it cannot vectorize this code. But if you just use this particular order of evaluation semantics, if you notice, this particular body is reading and assigning simultaneously. And if you use these semantics of C, you will be able to identify aliasing relationships that will allow the compiler to optimize this. And in this particular case, if I recall correctly, there was a significant speed up, maybe around 6x or something like that for this particular benchmark. And that's huge. So now the question is, why would C designers choose such semantics? Why did they leave the order of evaluation? So first of all, I hope I have established that using these semantics, I'm able to identify aliasing relationships and I can improve code. But then why did C designers choose this? And the question is, the answer is, C was designed in 1989, where in every cycle was important. From 1989 till 2019, what has happened is computers just kept getting faster, at least a large part of 2019. And so people just forgot this art of doing optimization. And now we are again getting saturated because of computer speeds and Moore's law. And now we are going to go back to those ideas. And so the surprising thing is that even though the C designers in 1989 had the foresight to develop such semantics so that the compilers get exploited, none of the production compilers, even after all this complexity, were using this, using this such a mechanism to improve performance. And our work was the first one to do this. So is it relevant today? And the question is, what are the possible performance improvements and how commonly are programmers coding such patterns? I mean, although it is part of the C and it's possible to do it, how much improvement? I've shown some examples, but in general, what is the improvement and how commonly is such code found in real world? So more generally, non-determinism is generally considered evil over the past 20 years. I hope I'm not running out of time.
I'm sorry, but actually hit the time. There is a question, and I think we can just wind up after that. Maybe the software equivalence checker we use across programming languages. There are lots of better programming languages where developer need not deal with basic nitty-gritties, but the industry remains stuck because of legacy. Can this study be extended to transform legacy code to more advanced and simpler development models? This is a question from Ankit.
Yeah, I mean, absolutely. This is exactly the thing that, one of the reasons that prevents software development models to kind of evolve is basically the lack of proper infrastructure to do optimization automatically. And indeed, better optimization support, in my opinion, is going to have an end-to-end effect on the software ecosystem and improve, allow automatic development of higher level models. And so, I mean, this is kind of, fundamental research and people are going to make improvements and we are just making some steps in that direction. I don't know how long it's going to take, but I definitely see this happening in future.
All right, maybe some final thoughts because we are already out of time. You can probably wrap up your session if that would be.
So by the way, I'm sorry. Somehow I just lost track of time.
No, it's all right. It was as if we were transported back in time to our undergraduate classrooms because I could see a lot of the code which was very simple, but the way you explained, there was so much complexity involved even in simple chunks of code. So that just goes to show compilers how important and how they're evolving nowadays. So some final thoughts maybe on where you see this going and what is your opinion about this.
Yeah, so yes, I mean, I think that people, lots of researchers are working in this direction. Our group is also working in trying to develop automatic algorithms to do this. I would encourage you to look at our portal called compiler.ai, where we basically do host demos as and when we are available. And yeah, I guess I hope I've already made my the summary of my points. Yeah, great.
That was really nice. And yeah, compiler.ai, I liked one of the terms, the ooh la la, that was a nice name given for order of evaluation based execution. That was a really nice name to come up with. And yeah, compiler.ai, I think everyone should definitely check it out. Thank you so much for giving us a complete breakdown of how compilers are working and what you guys are doing as well. Thank you, Professor Saurabh Bansal from IIT Delhi. And this is your virtual memento. Thank you for being with us here at IEEE Data and Storage Summit.
Thank you. Thank you.
Thank you so much. All right, then, with that, we will now move on to the next session of the day, and that is going to be data and compute challenges at the edge. And the penultimate session for the day would be conducted by Jean-Francois Marie from the board of directors. He's the board of director of SNIA EMEA. Over to you, Jean-Francois.
Hello, guys. Can you hear me well?
Yes, you're very clear and can see you as well.
Okay, very nice. So I need to share my slides. I need to look at, okay.
You should see a share button. Yes.
Yes, coming here.
Yes, we are able to see your screen.
Yeah, and you're gonna see my presentation here.
Yes.
All good? Very nice.
All good.
Okay, thank you for the time. Happy to be there. So let's move forward because we have only 30 minutes to spend together. So this is a bit of my background. So I'm Jean-François Marie. I'm a Chief Solution Architect at Calray, and I'm going to introduce the company very briefly. I'm very happy to follow an AI pitch on compilers because this is what my company is doing. And I'm participating in a SNIA EMEA. So I've been 30 years in the data center industry in various roles, acting as a volunteer for SNIA for many years as well. I was leading the French organization for 2 years, and then I'm back to SNIA, participating in the EMEA movement, right? Calray, just quickly, it was interesting. So Calray is a French company, it's a French startup, 10 years old. We are doing processors, and one of the functions of the processor is doing AI and convolution networks. Very interesting to see those compilers option because my company has developed his own core, his own compilers, his own SDK. So very interesting to see all those optimization in the pitch before. So we're doing processors, we are doing boards with two categories. One, to do embedded world for autonomous driving. We have 3 cars running in the world today with our processor. It's a lot about data treatment, AI, intelligent making decisions. I'm going to cover that. It's kind of an edge, right? A car is an edge. This one on the one hand, so everything about compute, acceleration, matrix computation, this is what we are doing. On the other hand, because we have a lot of compute power, we can do 5 TOPS per processor. We have 80 cores. We are doing computational storage. So we are doing NVMe, NVMe storage, NVMe OF, and all those inline hierarchical coding. Just about my company, now moving back to the pitch. Some legal notice. SNIA, for those who don't know SNIA, SNIA is an industry organization. You see here, we have about 2,000 active members to write some standards in terms of management, for instance, Swordfish, but there are many of them you can see, so SNIA.org, and you have more than 50,000 IT end users and storage. So this is individuals. It's a free contribution. If you want to participate in technical work groups, I'm more than happy, or your company can sponsor the organization. We are here to educate, to support, to understand and collaborate, right? Though there's no profit made by the organization, it's just really to promote the storage technology and how it moves and set new standards. So here's the agenda for this morning. I'm going to go through some data challenges I see, speak about AI a little bit because I think this is really one of the hot topics when it comes about doing some analytics around data. I'm going to share with you some views about edge topologies very quickly, and give you a quick sneak view on 5G, which is also a big topic. And you see, you could see how difficult it is and complex it is. I'm going to speak about NVMe because it's really another hot topic, changing the world in terms of storage access, and some ideas in terms of the things you can develop or do differently. What are the data challenges? And I think that's important. And you know, this subject about the compilers of optimization to do AI, etc., is interesting. I've been, you know, in NetApp for the past 30 years, and I was curiously trying to understand the data flows for AI, and what are the job of data scientists? What are they doing to make sure that we train the networks in a great way so that the network can make decisions. So it was for proactive maintenance. And we had exactly what's happening on that slide here, collecting massive amount of data. The company had like 1 million systems connected in the world, generating petabytes of data per month. And the problem when you try to do something with that data, it's like oil, right? We used to say data is a new oil. What does this mean, right? It means that oil is the natural thing you get, like data, you get it, but it has very little value, right? Until you transform it. If you transform oil in petrol, then you get value because you can use in the cars. The same with data. If you do nothing with the data, you cannot get anything for your business, for your applications, etc. So you need to treat data, you need to filter data. And this filtering activity will be more and more important. And by filtering, it means understanding the data. And what I've learned for the past years is data scientists are spending 90% of their time filtering data because there's too much data you can filter. If you go to CERN in Switzerland, right, they have this loop accelerator to do to break particles, understand how Earth, the Big Bang, right, the Big Bang theory. The problem they have is they can only analyze 10% or less of what they see as data. They have to filter. And it's not an easy decision. And the problematic we see with edge, because all that type of data being generated is only 20%, 25%, it's a lot, right? Already a lot, is going to go to the data center. The rest will be ephemeral. So either it just pass and you don't treat it, or you need to analyze it. That's a challenge. That's a challenge specific for the edge. Think about IoT, all those connected devices. 70% of what you create will disappear. Think about what you do yourself. When you take pictures with your camera, how many of those pictures are you effectively managing? Are you computing? 1, 2 on 100, 1%, 2%? Exactly the same for data. So this is the new challenge for companies. It's good to collect, putting cameras everywhere, but it's better to do some analysis, and that's where the challenges are. If you think about AI, the question is not, shall we do, but the question is, when will you do, right? A survey has been run by some consulting companies like Accenture, McKinsey, and like KPMG, right? What they've seen, there are 2 types of customers. The one who will adopt AI and the one who have adopted AI. So the question is, what is AI, right? Is that just an algorithm? Is that just a filtering? There's so many flavors. So it's important to say, hey, when we do AI, this is what we're going to do in AI. Is that computer vision? Is that fault detection? Is that machine vision? Is that networks? So many flavors. So it's important to define what is AI, what is that you want to use. The other thing is, as I said, vast amount of data. The problem is in many companies, there are data silos. And it's about mathematics and probability. If you want to, you need a good samples to find something. The larger the samples, the best. But if you have data silos, then the problem is you cannot get anything about it. So when you think about large companies, you have many departments: the sales department, the marketing department, the engineering department, the manufacturing department. They're all generating data, right? But at the end of the day, it's to serve one customer. So it's important to reconciliate that amount of data to make something which is relevant for a given customer. Unless you do that, you don't get a 360 view. So first, for many years, data have been in silos for many reasons, security, department segregation, etc. The challenge with AI is you have to first put that into one big data lake. The other thing is the poor data you may have. And it's very trivial to see that in AI, when you train your network, all the BAs you may have. That's really a challenge. If a European Caucasian face guy is training an algorithm for a car, this car will only recognize as pedestrian, Caucasian, not Indian, not American, not Japanese, not Chinese. That's a BAs, because of the data is too poor. The other challenge is, nonetheless, you have too much data, you have to filter. You have silos, but you need the right samples. That's important. So perhaps what the amount of data you have is not enough with regards to those samples and the variety of data to train what you want to train, right? That's another challenge. If you think about AI, what is the aim? Basically, the dream, let's say, if I can say, if it's a dream, right, is to get machines to reproduce the human brain. Let me tell you something. I had 2 years ago a very interesting chat with the Siri inventor, Apple Siri, right? It's a French guy, Luc Julia. He told me something very interesting. How efficient it is, because we have this ability to do a lot of things. How efficient is the brain? How efficient is the most intelligent, if I can say that, AI algorithm? Let me give you 2 examples or 2 figures. From your perspective, how many cats a child needs to recognize a cat for his life? The answer is 3. How many cats the most powerful AI algorithm needs to recognize a cat? 100,000. And it may only recognize with an effectiveness of 95%, right? So it's not efficient yet, and far to be efficient. And in terms of power consumption, the brain is using 30% of the energy we consume. So when you compute a lot in your brain, you're angry, you need to eat, right? If you think that, you take that 30%, imagine we move all data centers to embrace AI. It means that AI will have to take at least, if it is as efficient as brain, 30% of all the power. So there's no power, electricity power on Earth enough to do AI unless you filter, you have the right data samples, and you have the right compilers and algorithm, right? Obviously, in terms of data intelligence, there are many threads, etc., coming. It's important in terms of the wording, right? AI is really the global thing. My perspective is AI is all about data analysis, and it starts with Excel. If you do Excel and filtering, you do some kind of analysis because you start to understand your data structure. Machine learning is you start to train a machine, but this machine will just repeat things. And deep learning, this is where you have neural networks. A machine will become intelligent, if I can say so, making decisions on a machine learning, no decision, just acting, learning pattern, right? It's important as well to see the challenge around AI, if you want to go there. Edge AI, having the data, the silos, making the decision, filtering, etc. It takes 4 to 5 years for any company to have an AI project running. You cannot get started, hey, I'm going to do AI, unless you have started to understand your data, to filter your data. So that's where it has to start, right? Data analytics means understanding your data. If you don't understand your data, no way to start with AI. You need to start there, right? Long process, interesting processes, complex processes. Market is huge. I'm not going to spend too much time on that one. And you see here on the left-hand side of the slide is really all the things you can do with AI and the different type of algorithm, etc. Have a look if you're interested. Perhaps you're super expert in it and use that perfectly. Algorithm, compute power, very interesting. And this is what's coming in terms of challenge. CPU, x86 ARM AMD are not suitable enough for deep learning. You can do AI, of course, with CPUs, but you need GPUs like system because they have been optimized to do matrix computation, and you need to go there. And we will see that for data to be efficient, another challenge is x86 power. x86 power is very high when it comes to compute data, and you need to have an alternative. And this is why we see GPU. We have seen GPUs coming for the past 5 years, and now what you see coming is GPUs, data per unit, because they have been optimized to do data processing. When it comes to edge, obviously the cloud is there. When I say cloud, it's all those devices connected in the world, right? 4G, 5G, fiber, whatsoever. And a device could be a manufacturing, could be a phone, could be a ring, could be a car, could be a fridge, whatsoever. So all those devices connected in the world generating data. What we know for sure, as I said, this data can't go to the data center. You have to filter. And the edge, if you take the AI definition or the AI data flow definition, edge is the first compute center where you're going to do intelligence. That's where edge is becoming more and more important. Coming back to the 5G example, for instance, at the foot of the antenna, you will get a mini data center doing data filtering, right? Because you need to track the phone numbers to make sure that you have the correct correlation with the antenna scope, doing some more features, etc. You need to have that intelligence there. And the challenge today is to put that intelligence at the edge to do the filtering while you don't have big data centers, poor cooling conditions, etc. To give you a perspective about 5G, this is how 5G is complex. Right. Start on the left-hand side. You have the phone. Whatever is connected with a smart computer will generate data, but then you have to translate that signal into digital signal, etc. And you have many challenges because then, for the operators to add value, right? They need to develop those applications, but it has to be vehicles in a secure manner. And the challenge with edge and IoT is you do not manage like in a data center. In a data center, you manage like thousands, tens of thousands of devices. With 5G and AI and 5G and edge, sorry, you will have to handle million, and not to say billion of devices, and the data flow will be more and more difficult to handle. This is from an edge perspective. If we look from a data perspective, we see also a big challenge, right? Because those data flows are very characteristic. It's not a single data flow, it's massive parallelism. My previous presenter mentioned determinism, right? This is important when you want to have a real-time answer. But massive parallelism is also one characteristic of AI. It's also characteristic of what's happening in terms of storage. What has been put together for the like 4 to 5 years is NVMe. Why? Because the traditional storage is completely locked, right? If you look at the numbers, when I'm speaking about billion devices, you can imagine how many IOPS you will have to deal with, right? For the 30 years plus, HDDs have been the bottleneck because they can handle only 100 IOPS also, right? But with NVMe, what happens? So NVMe with SSDs, now they can handle nearly 500,000 IOPS, 200 to 300 kilo IOPS per SSD. It puts pressure on the storage nodes. All the storage OS you may know, right? You push their limits. They have not been designed to handle those many IOPS, right? But this was led by SCSI attached, so serial connection. And an SSD is no more magnetical thing. There's no rotation. It's a pure memory. So it's suited for parallelism. And what's happening with NVMe, because NVMe is going to replace SCSI, it's going to take a while, but it's here, it's very mature, etc. is a highly parallel a way to access storage devices and SSDs. And the new generation SSD can handle 1 million IOPS per SSD. So it's breaking the whole stack. It's breaking the storage node, is breaking the compute node, is breaking the network. So you have two pressure. You have one pressure coming from the edge, billion of devices, data flows, massive data flows to handle. And you have a pressure coming from the data center, from the top of the data center, pushing you to review the full chain, because the IOPS managed by the new generation SSD is massive. And you have to combine those two things in order to have something consistent being running. And this is a huge effort, right, for the IT guys. So you've seen that. Have a look. NVMe Express is the organization which is defining NVMe. And look at the change, right? When you think about massive parallelism, SCSI 1Q, you can handle one command at a time. NVMe, you can handle 64,000 commands at a time, 64,000 queues in terms of IOPS. This is massive parallel. So think AI, Edge, NVMe, all those things will drive a new type of compute power, which is massive parallelism. Obviously, a new network, NVMe OF, to handle this massive parallelism across. Many applications, I will not go spend time here, but obviously those applications take benefit of those new parallelism. So what could be done? What we see, what project we are working on, you need acceleration. The promise of storage defined or software defined was there, and it can't be handled anymore, right? You need to do acceleration. You have seen GPUs, as I said, for AI, you need those hardware devices to accelerate, and it's going to be the same for edge. At the edge, you're going to need hardware assist power in order to treat all that type of data. Either you want to do machine learning at the edge, or you want to do just inference. You want to have smart NIC to handle security. You can handle security by software if you have to manage tens of thousands of encryption for guys like users. But it's impossible to think about software security for billions of devices, because the x86 power will be too high. You need a super efficient engine in terms of how you treat the data, but how much power you consume, right? There are many data centers in the world lacking electricity. So and for the planet, I think there's an urgency really to think about power. So optimization, algorithm optimization, power optimization, compute optimization is really at an edge of all those things, right? When we put them together. You need to think about the data processing unit, right? They have been designed. This is not a generic x86. Those are like co-processors, accelerators as companions to x86, or having this ability to do millions of IOPS with inline processing. To give you a perspective, I've been in the storage industry for years, but until last year, the most powerful storage array could deliver 2 million IOPS per node. Today, with NVMe and NVMe OF, what you see on the market, we are speaking about 14, 20 million. So it's 10 more times more powerful. So it's breaking a lot of things. Many companies have to reinvent themselves. And then computational storage is one way to handle this amount of data. You put, as you know, there's a rule: the closer the CPU, the faster. If it's a physical law, right? You cannot change it. So you have two ways to do it. Either you put the compute to the data, or you move the data to the compute. And computational storage is when you store your data on your drive, very close to that drive, you're going to do the compute, and not far away, in a data center, etc. This is not going to work. So optimization, super specialized computers, put data very close to the compute, or put compute to the edge in order to treat that data, are really some directions in terms of the thing you can do. Here you go. I think I'm on time.
That was brilliant, on time. And Jean-François, we do actually have a question for you. And the question is, the devices at the edge could be IoT, but they themselves could be vastly varying in capability. How do we create standards on implementation and data analysis for such vastly varying devices?
That's a very good question. That's where it's very difficult, right? Because the vast majority of the type of data you're going to see is where it's getting complex to train algorithm if you want to do AI, right? So that's where intelligence will take into account to invent new things, right? But if you take one company at a time, that's where it's impossible to say, I'm going to do IoT and do a lot of things. For instance, you're going to, let's take an example. I think that's more interesting. You want to install cameras because you want to do video surveillance. You can say, hey, I'm going to film black and white. It's enough for me. And then to change it to 3D, face recognition with enhanced AI algorithm, etc. That's a change, even though if it's the same thing. You're right. It's a change of capability. So to handle it, it's a full process of revisiting all the tools you have, etc. So it's a lot about mathematics and what's happening in the world. Some companies like Amazon, the big GAFA or BAFIX, because they don't have data silos. Their force is they don't have data silos. They have a massive amount of data. They have this variety of data. And what they have recognized is this exact difficulty, which is what is the best algorithm to treat my data? I don't know this format. What should I do? So this is quite a challenge. I had a presentation with Amazon last year, and they were explaining that what they're doing now, what they're providing to their customers is not just AI algorithm, or not just the algorithm. They say, hey, this is a toolkit of algorithm. Give me your data. Give me your data sample, and I'm going to provide you with the best algorithm for your data sample. So big companies, that's where it's important about, not having silos, regrouping, having this ability to have all sorts of data, understand them, is to be able to find the right algorithm. And some companies are already doing it. So one solution would be reach out to those guys because they have one way to treat it, or do it yourself. That's where, for India, for instance, it's also a challenge, I think, is how much data India in itself is generating. Are there AI challenges in India in order to collect and provide those new algorithms? So unfortunately, it's only the big guys who have this ability to provide a new algorithm because they have the variety of data and they can learn from that. If you are a single company, it's going to be a challenge. You're going to learn by yourself or being assist. I hope it gives you an answer, but it's not an easy one.
Thank you so much, Jean-François. And it was a pleasure having you here at the IEEE Data and Storage Summit 2020. This is your virtual memento. Thank you for sparing your time and enlightening us with a lot of information regarding the IoT world. And we definitely look forward to meeting you again. Thank you so much.
Thank you very much. Have a nice day.
Thank you.
And a nice session as well.
Au revoir.
Au revoir.
All right, and with that, ladies and gentlemen, others, we come to the last session for today. And the session is going to be NVMs in the memory hierarchy from smartphones to servers. This session is going to be conducted by Professor Manu Avasthi, Associate Professor of Computer Science, Ashoka University, and PhD from the University of Utah. Over to you, Professor Avasthi.
All right. Thank you very much, Anvit. Thank you to the IEEE Bangalore Section and Huawei for giving me the opportunity to speak here. Let me just try and share my screen. It might take a while because apparently the hardest problem in computer science today is how to share your screen.
Well, when you're not hearing the other person.
Absolutely.
But you are audible, you're clear, and we can see your screen now. Over to you.
Excellent. All right. Thank you very much. Thank you for the very warm welcome. What I'm going to talk about today is essentially trying to find a place for non-volatile memories in the memory hierarchy. I also know that I'm the only person standing between everybody and lunch, so I'll try to be quick. Most of the work that I'm going to present here is essentially being done by one or the other of my student collaborators. I have listed them out over here on the bottom of this slide. I am the one to be given the talk, but the bulk, or essentially all of the work that has been done that is going to be presented in this talk is going to be, or has been done by the students that have worked with me over the past few years. Right? So there's a standard disclaimer that I do before I start any talk. Given that I'm a systems person, I do want to make it clear that this is a talk about memory hierarchy design using non-volatile memories. And given how things are today, what I want to make absolutely clear is that this talk is not really about machine learning, just in case somebody in the audience was wondering. Right? Okay, so my central thesis for the past few years about designing memory hierarchy, especially trying to use NVMs for that, is to sort of have a top-down approach in the sense that while trying to design newer architectures for both memory and storage, what we should try and look for are insights top-down from the application space and from the system software space. And I'm going to give a few examples from some of the recent work that we have done to support this central thesis that I have. Right, and I'm going to talk briefly about two different verticals. One is essentially the vertical of handheld devices, and the other one is the vertical of memory hierarchies in servers. Let's start with handheld devices. I mean, as everybody knows, handheld devices are everywhere, from smartphones to tablets to wearables and everything that's there in the middle, right? So the proliferation of devices has been relatively very, very quick. A lot of these devices have been running on some version of open source system software, predominantly Android. And system software over the years, I'm going to take Android as an example. Since the time it was first released in 2008 to the time till this slide was made, which is around 2016, it has had almost an yearly release cycle, and every year around the end of the year, major revisions to the operating system, specifically Android in this case, have been more newer feature-rich applications have been made possible. Right, and I'm going to take a few examples and talk about some of those applications and how their behavior in terms of their memory requirements has been changing over time. So in this particular chart, which is from a couple of years ago, it gives you an idea about the memory capacity consumption of various mobile browsers. On the y-axis over here, you have all kinds of different types of browsers that can run on mobile devices. On the x-axis over here is the amount of memory they consume. The blue part is the amount of memory capacity they consume when you were just running a single tab and not loaded anything into the browser. Whereas if you look at the blue plus the orange bar, which is this entire sort of horizontal bar over here, you will see, or this is the combined capacity of 5 tabs, and 5 tabs have been loaded with some sort of a web page in there. As you'll see, depending on which browser you are using, you can end up consuming around 400 on an average, 400 megabytes of memory capacity on an average, all the way up to 700 megabytes. And this is one of, and I took mobile browsers as an example because this is something that almost all of us use on our mobile devices. Right. So again, the point that I sort of want to drive home over here is the fact that even the simplest of applications have decently high enough memory capacity requirements while they are running. Right. Similarly, is the case with more feature-rich applications. For example, things like games, PUBG as an example over here. While it is running, it tends to consume around 1.1 gigabytes of memory capacity. Right. And as you can imagine, when you have a smartphone system where you are multitasking various things, you have a game running in the foreground, you have a few applications running in the background, the total amount of memory capacity that you'll end up consuming is going to increase significantly, and that is going to increase over time. And this is something that has been projected by the financial analysts as well. So what I want you to concentrate on in this case is the second bar over here and how it moves over time from 2010 to 2015. This second bar over here gives you the amount of memory capacity for the top smartphones in the market and how that number has changed over time from 2010 to 2015. I know this data is a little old, but it'll give you a sense of how fast things have been moving. In 2010, the average top-line smartphone had around 330 megabytes of DRAM capacity attached to it. In 2015, this was, and at this time, this was a projection. This was projected to be around 5.7, approximately 6 gigabytes, which is essentially what is happening today. So medium to high-ish end smartphones tend to have around 4 to 6 gigabytes of memory capacity attached today. And that is a testament to how things have changed from the application perspective, how they have become or have larger working sets. And how the system software as well has evolved to kind of support these feature-rich applications. Right. In order to keep up with these capacity requirements, of course, the memory vendors have come up with more dense chips. So on the left, you will see some of the screenshots from various companies about how they have come up with chips that are more dense, and this capacity per chip has kind of been increasing over time, right? So that's one part of it. The capacity requirement of all of these energy consumption, which is also a central design point for the smartphone market, right? So this is a distribution of where in a smartphone is the energy being consumed. And as you will see, this gray, the orange part of the pie chart over here, which is labeled memory, tends to consume around 25 to 40% of the total energy consumption of a particular handheld device, depending on the type of applications that you are using. So Skype consumes around 25%. There is a multiplayer game that tends to consume around 35%, right? So again, a large part of your energy in your smartphone is essentially being consumed in the memory subsystem. And if I project the increasing capacity over time into the future, this fraction of energy that is being consumed in the memory is also projected to increase over time, right? So what I've covered so far are essentially some of the trends in the handheld market, which sort of talk about how applications are becoming feature rich, which essentially means that there is need for larger memory capacity because each individual application requires more capacity, right? And the memory subsystems over time have started to increase as a percentage of the total system energy, more and more energy over time. And this is projected to kind of increase over time as well, right? So what we want is essentially more capacity, but what we want on the other hand is a memory subsystem that consumes less amount of energy, which are kind of orthogonal goals. I mean, the more you increase memory capacity, the idea is that you will end up spending more energy. And the reason for that is that most of the capacity for modern handheld devices comes from some version of DRAM, which is essentially known as low power double data rate or LPDDR DRAM. This is a modified version of commodity DRAM. It is geared towards saving energy as compared to the traditional commodity DRAM, but at the end of the day, it is still a dynamic random access memory, which essentially means that there is a refresh that still needs to happen every once in a while. Also, depending on who you ask, DRAM is beginning to get towards the end of scaling. So 10 years ago, people projected the end of scaling of DRAM at around 40 nanometers, but it has kind of still grown strong, and it is still on the market. But at some point in time, physics is going to catch up and DRAM is going to stop scaling. Right. So here is where things stand right now. Smartphone applications require more and more memory capacity. The more memory capacity that you provide these smartphones in terms of DRAM, the more energy it will end up consuming. And at some point in time, the DRAM is going to stop scaling. So the automatic capacity benefits per unit area that were coming because of scaling of DRAM are going to go away at some point in time. Right. So what do we do? The idea is at some point in time, around 10, 12 years ago, people started looking at what are the alternatives that we can potentially use in place of DRAM. And the answer was to look at that point in time, what were known as emerging memory technologies, which were also just by sheer luck, non-volatile in nature. Right. So if you look at the choices that are available today, you have 3D crosspoint, you have phase change memory, you have STT-RAM, resistive RAM. There are all kinds of different options that for providing the characteristics that I have just mentioned a few slides ago. I'll also mention here that our non-volatile memories are not a recent phenomenon. They have been around since the 1960s. It's just the circumstances of our devices have changed to the extent that we have started looking at all of these new technologies as a potential replacement for DRAM in the main memory. Right. So again, although all of these different options are there, what they fundamentally vary in is the way in which they store information. Right. So if you recall, DRAM fundamentally stores information as charge on a capacitor, whereas all of these different non-volatile memory technologies are resistive in nature, which essentially means that they store information as either a high resistance or a low resistance. Right. And again, most of these non-volatile memory technologies have certain characteristics of their own. Some are good, some are bad. The good ones are essentially easy to enumerate. The first one is there are many candidates out there. So if you have, or if you want to pick a particular type of memory technology for designing an architecture, you have many choices to pick from. They have higher areal density, so they can give you more capacity per square area as compared to DRAM, and have very little refresh or standby energy. But at the same time, they have their own drawbacks, which are essentially higher access latencies as compared to DRAM. They have asymmetric read and write energies as well as latencies, right? So in DRAM, the amount of time it takes to read and write is approximately the same, whereas if you switch to any other NVM, of the ones that I have mentioned in the previous slide, they have asymmetric read and write latencies as well as asymmetric read and write energies. The other bigger problem with non-volatile memories is that they have limited write times, or limited lifetimes rather. So you can only write to a particular cell n number of times before the cell kind of wears out. So here's a nice table that I have picked up from the paper from Mittal et al. That was published in 2016 that gives you a nice comparison about various features and potential drawbacks of various kinds of memory technologies. Right. So just to give you a quick example, when I said that information in these NVMs is typically stored differently than DRAM, I'll just quickly pick phase change memory or PCM as an example. In PCM, the information is stored as resistance. PCMs are typically made of what is known as a chalcogenide material, and by the application of current and deciding how long a particular amount of current has to be applied to this particular cell, the chalcogenide material can either exist in the amorphous state, which is essentially a high resistance state, or in the crystalline state, which is essentially a low resistance state. And then you can associate high resistance with the bit value 0 and low resistance with the bit value 1, or the other way around. right? So again, and that is also this application of different amounts of varying amounts of current is the reason why in the case of PCM, it tends to have limited lifetime. So I'm not going to go through this slide because this is essentially what I had just mentioned over there. But the fundamental question when it comes to designing memory systems using NVMs becomes this, right? So we have certain plus points for these NVMs. We have certain negative points for these NVMs. And as far as our overall system design is concerned, we have a certain amount of design codes, specifically for handheld systems. What we need is essentially something that gives us large capacity, that keeps the latency low, that helps us reduce the overall energy consumption of the memory subsystem. Right. So essentially what we have to do is we have to use the pros of NVMs to our advantage and design systems in a sense that we are able to overcome the cons. Right. So if you traditionally look at how NVMs can fit into the memory hierarchy, there are by and large two schools of thought. The one on the left is what I have mentioned as the single address space paradigm, in which what you or what designers decide to do is to split the entire memory address space across multiple types of memory technologies. In this particular case, I have shown the address space being split between DRAM and NVM. And the other one is the case where you can have the DRAM as a cache for the NVM. Right, so I'll give examples of both of these things as ways to sort of fit NVMs into the memory hierarchy. Right, so if I look at a traditional architecture or the memory architecture in handheld, you will see a bunch of cores. You will see a bunch of sort of IP units. In this case, the GPU, sensors, the modem, so on and so forth. And then they are connected via some fabric to a memory controller, which then is connected to the DRAM DIMMs using buses or channels. Right. So in one of the works that we sort of explored a couple of years ago was trying to look at application characteristics of smartphone devices and trying to see if we can somehow change this basic architecture to use NVMs by gaining some insights from how applications behave. So we characterized a whole bunch of applications. And what you see in all of these graphs is essentially which addresses of a particular application's memory space were touched more as opposed to which were touched less. Right. So on the x-axis in any of these graphs is time. Application run starts here and every time an application touches a memory address, it is marked with a dot. And these areas that have these concentrated lines or these black regions are the memory regions that are touched the most by any application. And if you look across multiple applications, you will see that certain patterns start to emerge. There are certain areas that are accessed a lot by almost all of these applications. And there are certain areas that are almost accessed negligibly in most of these applications. Now, if I was to design a naive memory system that can use this insight to just create a memory hierarchy using NVMs that is high capacity, what I would end up doing is to make sure that all of these highly accessed areas of memory are attached to a memory technology which is low latency, for example, DRAM. And all of these memory regions that are not touched or not accessed as much are attached to memory technologies that is probably high latency, but also high capacity, which essentially means that my overall memory hierarchy is going to have high capacity overall. And that is essentially what we ended up doing. So we had this total address space, which was, let's say, from 0 gigabytes to 4 gigabytes. And then we broke up these address space or the entire address space into what are known as sub-address spaces. And each one of these sub-address spaces were affiliated with a particular type of memory technology using a memory controller, right? So I could have one sub-address space attached to a DRAM, the other one to some NVM, and the third sub-address space attached to something which is, let's say, a phase change memory device. And this is actually something that we published a couple of years ago. And now you can see the change in the architecture where what I used to have was a monolithic memory controller that was just controlling DRAM devices, has now been broken down into two memory controllers that controls a part of which controls the DRAM and the other part of which controls the NVM. And the idea is that the combined capacity of my memory subsystem is going to be much, much larger, given that NVM has larger capacity as compared to DRAM, right? And I can keep on doing this. I can keep breaking my address space into smaller and smaller sub-address spaces and keep handling different types of NVM technologies, phase change memory, STT-RAM, whatever have you, from these sub-address spaces, right? So overall, I get a memory hierarchy or a main memory which has higher capacity. But of course, there are going to be performance implications of this design choice, given what I had said earlier, which is essentially NVM, specifically PCM, for which we did the evaluations for this paper, tend to have higher access and sometimes higher energies. So what we ended up seeing, essentially, there's a lot of data in this slide, and I don't want you guys to look at all of it. What I wanted to look at are these two graphs, or these two lines over here. Is the first one is the one in which I had two sub-address spaces, and both of them were controlled by or were comprising of DRAM. And the other one, which is this green line over here, which is essentially two sub-address spaces, and both of them were comprised of PCM. And these lines over here are signifying relative energy consumption for each one of these different benchmarks that I have listed on the x-axis. And you'll see that between the green line and this purple line over here, there's a large differential in energy, right? So which essentially means that if I end up naively replacing all my DRAM with some sort of an NVM, I'd end up saving a lot of energy, right? But the other thing that I sort of should also mention over here is that the overall access time also tends to go up, right? So if I just naively replace all of my DRAM with something like PCM, which is signified by these the relative height of the blue bar and the green bar over here. So the green bar is where I have replaced all of my DRAM with PCM, and the blue bar is where all of my memory is actually DRAM. And you will see the overall execution time kind of goes up between these two. So I win on the energy front, I win on the capacity front, but I lose out on the performance front, which essentially means that there is something more that needs to be done in terms of intelligent data placement, which is something that we haven't done yet, but we are working on right now. So what I want to sort of everybody to kind of take away from this is, one, NVMs can be integrated into the handheld memory hierarchy. We can provide mechanisms to have a high capacity and low latency memory hierarchy using NVMs. But in that case, we would have to change potentially the system software as well to make sure that intelligent management of data happens such that your quote unquote hot data is essentially kept in a lower latency memory technology, such as the DRAM, which essentially points to doing something like a hardware software co-design kind of an approach, which is essentially something that we are exploring right now, right? So, okay, this was the part of the talk where I was going to focus mostly on handheld devices and how NVMs can fit into the handheld memory hierarchy. Now, let me quickly switch gears and try and talk about how NVMs made to fit into designing memory hierarchies for servers as well. Also remember what I had talked about previously for the handheld domain was essentially the paradigm where I had talked about how the single address space, which is comprised of various kinds of memory technologies, can be used to our advantage to create a high capacity and low energy memory hierarchy. In this case, in the case of the servers, what I'm going to talk about is how to use the DRAM as a cache paradigm that I had talked about to create high performance memory hierarchies using NVMs. Right. So this is just a motivational slide over here that tells you about the various kinds of applications over here on the right hand side that are typically executed on server platforms. And again, as probably everyone knows here, these are the workloads that require a lot of memory capacity. And again, this is something that is, or capacity requirements of the server workloads as well, is not something that can be met by just using DRAM, because over time, DRAM is going to stop scaling, right? So as I said before, in this particular case, what I'm going to talk about is how to sort of use the DRAM as a cache for the NVM paradigm to design high performance memory hierarchies using NVMs, specifically for server workloads, right? And again, most of the insights that we are going to get to design these architectures are going to come from the analysis of the workloads, right? So the state of the art DRAM as a cache implementation, which is known as an alloy cache, right? So alloy cache is a design for D12, and what in a nutshell this design is essentially a direct mapped cache to the NVM. Is located in the DRAM that sits next, or that sits between the CPU and the NVM, which acts as the main memory. The same still fetches data at a cache line granularity, and line's case is 72 bytes, which consists of 64 bytes of data and 8 bytes. Not going to go into this in the interest of time, but let me quickly point out some of the interesting insights that we found while kind of analyzing the behavior of various workloads with respect to alloy cache. So we set up a simulation system using NVMain and ZSIM, in which we had 1 gigabyte of DRAM cache and 64 gigabytes of PCM, and ran 8 instances of various parsec workloads. What we figured out that for all the pages that were present in, or all the pages that were accessed in the NVM, almost 80% on an average of those pages had 1/3 of their cache lines accessed. And there were many pages in which almost all the cache lines of a particular 4 kilobyte page was accessed. So one of the things that we sort of got from analyzing these workloads was the fact that workloads exhibit page level spatial locality in NVM, right? So that was one with the alloy cache in place. So that was one thing. Now the other thing was us looking at the utilization of the capacity of the DRAM cache. Remember, we had the alloy cache, which was 1 gigabyte in size, and what we looked at was, well, how many of the pages, or how many of these 4 kilobyte pages that are present in this 1 gigabyte cache are actually being used? The answer was not that much. On an average, 92% of the pages in the DRAM cache were essentially going unused, right? So if I sort of wanted to pages in my entire DRAM cache were actually being used, right? Pages were not being used, which essentially provides us some insight as to how to used portion cache to better or design a better memory hierarchy. And our idea was to use this space as something which can be used as a prefetch space for prefetching data from the non-volatile memory into the DRAM cache. What we proposed in this particular case was to leverage both of the insights that we have gotten from the previous experiments, which was essentially the presence of page level spatial locality and the fact that most of the region in the DRAM cache is mostly unallocated, and design a I'm showing over here. We have a few more components in our as well as the NVM memory controller. The salient point of this prefetcher was the fact that it could accommodate both alloy cache lines in the DRAM cache, as well as the cache or the pages that were prefetched from the non-volatile memory in the same DRAM structure over here. Right. So in the interest of time, I'm not going to go into the details. If you want to look at the details of this design, they're there in the hot storage paper that we just published earlier this year. One quick result that I'm going to sort of point out is, because of this optimization, we were up to 7x, which essentially translated into 14 or 16 to 40% higher accuracy for almost all the workloads that we had considered, right? So in this case, what I sort of want everyone to kind of take away from this was NVMs can potentially, in the case of DRAM as a cache variant, and what we proposed in one of the works that we have done over here is how to design a prefetcher that can effectively prefetch information from the NVM into the DRAM cache by making relatively simple changes to the DRAM and the NVM memory controller, right? So I'm almost out of time. Hopefully, there are a couple of things that I want everyone to take away from over here is that irrespective of the vertical that you're looking at, whether it is smartphones or handhelds, or whether it is performance or high performance servers, there are incorporate NVMe into memory hierarchy, and at some point in time it will automatically become a necessity. And what I always advocate for is essentially getting insights from how the applications behave and trying to kind of mold the architectures based on those insights. So again, I'd quickly acknowledge all the students who have primarily contributed to everything that has been done that I've presented so far. And these are the few funding agencies that have been kind enough to support our work. With that, I'll stop here and I'll be happy to take questions.
Thank you so much, Professor Manu Awasthi. Very in-depth talk over there about where we are heading with respect from smartphones to servers, NVMs. And I believe we have a question here from Ankit, and it says, with memories associated with different CPUs, we need to deal with NUMA, NUMA. Do you propose a programming model to developers to use and to be exposed to which address spaces are DRAM and what is mapped to NVMs? Any proposals to make this transparent?
That's a good point, right? So what we haven't done or dealt with over here is the fact that programming models also need to be cognizant of the underlying assumptions about memory have kind of changed now. So all the programming assumptions up until now just assume that memory was volatile and were made accordingly. But with the newer architectural changes in place, parts of the memory might become non-volatile, and essentially people who are writing application code might also need to be made cognizant of the fact that in simpler terms, this essentially is not the memory hierarchy that was present there before. Right, so NUMA is an interesting concern, right? So NUMA specifically is a bigger concern in the case of high performance servers, where the latency differential between the memory right next to me versus the memory that's sitting further away is 50% or more, and in typical DRAM, and that's going to increase even further as and when the devices that are attached to these systems become slower, so to say, or have higher access latencies. That's a good point. I mean, that is something that will definitely need to be addressed. At this point in time, I don't think I have a very good answer for that.
Thank you so much, Professor Manu Awasthi. And here is your virtual memento. Can we have that on the screen now, please? There you go. Thank you for sparing your time and speaking to us about this topic here. And thanks to all your students as well who have contributed on this paper. It was really nice. And we hope to have you here again at the IEEE Data and Storage Summit next year.
All right. Thank you very much.
Thank you. And with that, ladies, gentlemen, others, that's it from us here at day one of the IEEE Data and Storage Summit, brought to you by IEEE Bangalore Section, co-hosted by Huawei Technologies. This is day one that we have ended here, but tomorrow we're going to be joining again at 8:15 a.m. We have a jam-packed day again. We have 6 sessions plus a panel discussion and a keynote session as well. We look forward to join again tomorrow morning at 8:15. This is me, Anvit, signing off right here.